Okay, it's 10:28. So I thought that already 85 participants are there. So let me just start interacting with them so that we get familiar to each other. So I'm Payal Mukherjee from IIT Bombay, and I'm a senior project manager here. And I welcome all of you in this morning, exciting morning, wherein we are going to have industry readiness workshop today. So before we start with the presentation and before we go ahead, just let me know, just let me know who you are. So are you students? Are you faculty members? Are you some CFD enthusiasts who are just freelancing, or you are from industry, you have just joined the industry, or you have been quite long of experience in the industry. So let me just in the chat box, you can just type in student, or CFD enthusiast, or professional, or faculty. Yes, good morning all of you. Okay, student. Hello, Professor Vivek. PhD student, that's great. So for researchers and PhD students, the knowledge of OpenFOAM for CFD is going to be a big help. It's going to be very effective. Student, okay. Most of you are students, and Mr. Abhishek is a CFD professional. Welcome everybody. Another CFD professional I got, Sutirtha Sengupta. So I can see most of you are students, some of you are CFD professionals. Okay, so AFM, yeah, so Yash, Mr. Yash. AFM is also very well connected with the field of CFD. So I hope if you stay connected with FOSSEE, we can work together in the future. Okay, master students in China. Okay, welcome, Mr. Wakar Ali. So for the students who are doing masters and research, for them, this knowledge, this workshop will be very effective. Because even if you aspire to join the CFD industry after your masters or your PhD, OpenFOAM is going to be a big help for you. Okay, hello, Arbin. Hello, everybody. It's already 10:31, another 1 or 2 minutes, and then we will start because we are expecting a lot of participants to join. Dr. B. Srinivasalu, yes, hello. Hello, sir. Okay, so I welcome all the faculty members, all the CFD professionals, and all the students here, PhD students. It's a mixed crowd with a majority of students. Okay, mechanical engineering student, Dr. Shekhar Srivastava, postdoc fellow. Okay. Okay, so Mr. Vimal Raj. So after this workshop, I think you'll be introduced with, you'll be accustomed with OpenFOAM, and you can compare why we recommend learning of OpenFOAM and using OpenFOAM, rather than using ANSYS. So, yeah. So many of you are CFD professionals as well, and faculty. So welcome all. Okay, I think we can start. We have 124 participants and more are joining in. So I think we can start the recording now. Okay, so let me start with my presentation. So welcome everybody in this interesting and exciting workshop on industry readiness. So this is the first workshop offered by FOSSEE IIT Bombay for all the CFD enthusiasts, the students, faculty members, and CFD professionals, wherein all the advisory board members of the CFD team of FOSSEE IIT Bombay will be interacting with you through live lecture sessions They'll be sharing all the topics that they are dealing with in their professional life in the CFD field. Okay, so this is going to be a very interesting one because you will get a actual picture of what is going on in the CFD industry at the present times. And all these lectures will be followed by hands-on session by the CFD team members of FOSSEE IIT Bombay. So I am Payal Mukherjee. I welcome you all in this workshop. I am working as a senior project manager here, and I have joined with all my team members, Mr. Evan Fernandez, Mr. Paris Falkar, Mr. Maljil Situla, Mr. Pranay Pandey, and Mr. Nikhil Chidnavis. So all of them will interact with you. They will be demonstrating different case studies related to the topics that the CFD professionals will lecture in this workshop. And I really recommend that all of you please attend all the sessions. Please try to attend all the sessions because it is going to be very effective. See, we are recording this this session. We'll be sharing recording with you. But if you are connected with us live, that is the best way to learn. You can interact with the speakers, you can interact with the team members of FOSSEE, and that is how you can learn in a best way. Okay, so now let me go ahead. So before we start the workshop, it is very important to know who we are and what is the FOSSEE project all about and why are you here for the workshop. Okay, so the FOSSEE project is being developed at IIT Bombay. It's an acronym for Free and Open Source Software for Education. You can see there is a double E because FOSSEE was launched long back in the year of 2009. And we are still persisting. We are doing very well because this project is aiming at mass education on free and open source software, FOSS. Okay, so when it was launched in the year of 2009, we were only focusing on engineering education. That's why you can see double E. Okay, so now it is free and open source software for education, and it is for all the streams of education, not only about the engineering students. So we are there for the statistics students, we are there for the GIS students, for the animation, for some part of chemistry we are covering. So we have a long, a broad spectrum of audience that we are addressing, we are training. Okay, and this is about FOSSEE, and the FOSSEE project is funded by the Ministry of Education, Government of India. It's a flagship project which is going on in India because I am doubtful whether any other country, any other ministry, any other national ministry actually supports the learning of FOSS. Okay, and why our government is doing this endeavor, I'll come gradually to this topic. Okay, so we are working for, FOSSEE is working for the NME ICT, which is the National Mission on Education through ICT. Our aim is to reach out to each and every corner, each and every strata of the society, so that, where in some of the remote places of India, wherein the engineering colleges or general colleges system is not that strong, you don't get good teachers, there FOSSEE is there to help you, for the rural students as well, wherein you can get practical education on software that you can apply, that you can enrich yourselves with, and you can apply for higher education and jobs. Okay, so now let me come to what is FOSS and why the training on FOSS is so important, that our government, our Ministry of Education is funding this project. So see, FOSS is, it stands for Free, Libre, Open Source Software. So the word free is not only associated with the free of cost thing, the free of cost value of the word free. Yes, it is definitely free of cost. You can access all the FOSS free of cost. You can download it and you can legally use it because it comes with licenses such as GPL and BSD. These licenses are free of cost. You don't have to buy these licenses, just like you have to pay for, while using commercial software. So you can legally use this license free of cost. You can download, you can use it free of cost. That is one aspect of the word free. But there are other aspects. For example, you are free to modify the software. Third aspect is you can distribute the software. That is also you're free to do that. There is a liberty. That is the word liber in this open source software, the FLOSS thing. Okay, so you have the liberty to modify, you have the liberty to distribute the software, and you have also the liberty to distribute the modified version of the software. So these are the four aspects which are associated with the word FOSS or floss. Okay, and why should you learn FOSS? So see, there are many colleges in India, like tier 1 colleges, which are availing, expensive commercial software to all the students, so that they learn those software and they get a degree. But it is, it is a kind of shackle. It is a kind of, for example, if you are able to access your college library, and if you are able to access a book that is available only within the college premises, and you cannot take the book away, out of the college premises and use it. So the knowledge of commercial software is just like that. If you're habituated, if you are accustomed in using only the commercial software, it is a kind of, you are shackling your knowledge. Okay, so okay, so that is why we recommend the learning of FOSS or floss. Okay, and there is no guarantee that lifelong you'll be using the software that are being taught in your educational institutions. That is why, for example, tomorrow you can also, think about opening your own startup. Okay, and you suppose you are joining a company in which FOSS is used instead of the software that is taught in your colleges. Okay, so that is why we recommend the learning of FOSS as a mandatory thing. Okay, even if you learn the commercial software which are available in your colleges, please try to learn FOSS, as a parallel thing, as a complementary thing. Okay, and the training that FOSSEE imparts is skill-based and output-driven, which means we will be training you on the hands-on part of the software. Definitely, you will need the theory part. You'll have to understand the conceptual part. Behind the CFD thing, or if you're using OpenFOAM, you have to understand CFD, the theory and the concepts very well. And the add-on thing is that you will have to apply your knowledge of the software to produce an output. So here, the FOSSEE learners, the people who come to FOSSEE to learn the software, for example, we have different fellowship projects, we have internship project, workshops like this. So in this kind of training programs, the students actually learn the software and they produce an output in terms of, say, a small case study, a research migration. So what are case studies, what are research migrations, what are lab migration, etc. I'll come to it later on, maybe after this workshop. So it's important to learn this software very well, learn OpenFOAM very well through this workshop. So you can see different tiles over here in this slide. And if you go to fossee.in, and if you click any of these tiles, you will be navigated to the respective pages. Okay, I'll take you to fossee.in later, maybe after this workshop, and then I'll show you everything. And this list contains all the software, all the FOSS that is trained by FOSSEE project. And all of these are very, very important nowadays. So even if you are learning OpenFOAM today, I'll recommend you to learn Python. R is very important because it's a statistical analysis software that is used in the industry in heavily nowadays. Okay, eSIM is for electronics and allied streams. Scilab is a very it's a open source software alternative for a very well-known software, which is MATLAB. Okay, so I recommend all of you to please learn all these software. If needed, I can share you this table later on. We have DWSIM and Open Modelica for chemical engineering students. Okay, GIS, as I mentioned, that it is for the mapping and the GIS part. FreeCAD we are developing. Okay, so that was about FOSSEE, and now let me come to the workshop highlights. So there are some important things that you will have to keep in mind as participants. Okay, so number one, all these in all the halves of this workshop, for example, in the first half, in the second half, in all the sessions, you will be getting the opportunity to attend live lectures by the CFD professionals who are the esteemed advisory board members of the CFD team of FOSSEE. We have people from government sector, public sector, as well as private sector. Okay, they will give you the insights of the problems dealt with in the CFD industry. at the present times. And every lecture will be followed by a hands-on session, hands-on training session, demonstration session by the CFD team of FOSSEE. Okay. Yes, a very important part is the certification. So after this workshop, after you learn OpenFOAM, we will certify that you have attended this workshop and you have learned some part of OpenFOAM. Okay, but this certification is based on some eligibility criteria that will be set by the FOSSEE team, and it may be, so we understand that we are doing it in working days, and attending each and every session might not be possible. But please, you can take it very seriously, and please try to attend each and every session. As I mentioned in the beginning of this talk, that attending each and every session is very useful for yourselves for learning OpenFOAM. Okay, and this certification will be based on some attendance sheet that will be sharing in each and every half of the of this 4-day workshop. Please fill up this attendance sheet, because that is the only criteria of certification. Okay, and attendance sheets will be circulated in ad hoc times. We will not will not announce that every day at 11:30 the attendance sheet will be given. No, it is not like that. We want you to learn, we want you to pay attention to the workshop, to the hands-on sessions. Okay, and certification is an add-on thing. It's just a minimum thing, a minimum kind of recognition that FOSSEE is providing you. But the main purpose of this workshop is to enable you to learn OpenFOAM. Okay, so please take it very seriously. Please give your 100% in this learning section. Okay, so this is the schedule. I hope you all of you have gone through this schedule. We will start with Mr. Advait Gupta of Pandav Applications today, and then in the second half, Mr. Ranjit Desai will be there for the talk in the second half. And all these talks will be followed by hands-on training sessions on OpenFOAM. Okay, so tomorrow we will have Mr. Arnab Chakrabarti from TCS, then Mr. Pushkar Sheth from Wabtec Corporation. In day 3, we will have Mr. Nikhil Bhamare from CFD Baba Simulations Private Limited, and Mr. Harish Jayaraj from Codynamics. Then on the last day, day 4, we will have Dr. Joseph Prabhu from the Indian Register of Shipping, and Dr. Manabendra De from CSIR NAL. So with this, I stop my presentation. I stop my screen sharing. Stop, Karan. Okay, and I'll request Professor Chandan Bose to please take over and interact with the participants and talk to them. So Professor Chandan Bose is a PI of the CFD OpenFOAM project of FOSSEE, and he is leading our team. So, and he is a professor from the University of Birmingham, and he's also a visiting professor here at IIT Bombay. So over to you, Chandan. Mute her. Audio. Okay, actually, Professor Chandan Bose was supposed to join from UK. So it is 5 a.m. there. So I think he's taking some time to join. So we can have the interaction with him later on after Mr. Advait's talk. Okay, so I'll just take some time to, call Mr. Advait. Please allow me a 1 minute time. Okay, so sorry for the interruption. So now I welcome Mr. Advait Gupta. Mr. Advait Gupta is a member of the advisory board of the CFD team of FOSSEE. So Mr. Advait is a founder and CEO of Pandav Applications Private Limited. He has done his master's from Stanford University and is an accomplished engineering professional with exclusive experience in advancing CFD across various industries and academic sectors. So he is the leading developer of the world's first all-inclusive computational physics-based software for additive manufacturing called AM Prava by Pandav. This software is particularly adding immense value to the national defense systems now. So Mr. Advait has had the experience as a senior CFD engineer and AI engineer in the US and has played a key role in integrating CFD into research and industry worldwide as the global head of academic programs. So I think, now I'll just hand over to Mr. Advait. Mr. Advait, welcome to this session.
Hello, am I audible?
Yes, you are very much audible. So welcome.
Hello, hello.
We can start the session. We'll have Mr. Professor Chandan's introduction later on.
Sure. Thank you, Payalji, a lot for having me again. And before I start, just want to thank everyone for, especially the FOSSEE team, for organizing this annual workshop. Where you train students in open form and other activities. Um, uh, Basically proliferating open source software uh, in India across all sorts of institutes, and very happy to see familiar uh, speakers we don't often get to meet, but I think today is a good opportunity to get updated with what everyone else is doing. I see Dr. Chandan Bose, who's of course leading the FOSSEE initiative. Happy to see his listen to his talk and see his work. I see Mr. Ranjit Desai is there. He's doing a great work in the field of water infrastructure. I also see Dr. Manbendra, doing a lot of good work at CSIR, and other people as well. Uh, while we talk about some of the traditional industries where CFD has been used, I will today focus only on the additive manufacturing industry, and I find it quite intriguing. Uh, the complexity that goes behind understanding 3D printing or metal 3D printing processes is quite challenging. And let me share my screen before I proceed any further. Is my screen visible?
Yes, sir.
Okay. Before we talk about additive manufacturing, let's talk about metals. Let's talk about how we have been working with metals from centuries. And one thing we all have realized, we may have doors, windows, a lot of metal-based infrastructure in our own houses, and especially coming from the northern parts of India, where there's a huge swing in temperatures all the way from 0 degrees Celsius up to 48, 49 degrees Celsius. Probably people living in this part of the world feel this uh, feel the behavior of metals quite closely, where metals become brittle at low temperatures. They start creaking, they start cracking, and all sorts of defects, and they are very sensitive to any changes of the temperature. uh, Traditionally, we have been forging metals. Uh, Temperature gradients in such forging processes are quite broad and very. It's a very slow and gradual sort of process. Cooling is often left for the environment, or passive methods. Thermal history is not very aggressive, and the entire material experiences similar sort of heat exposure throughout the manufacturing. Okay, so the effect for all this is slower temperature responsiveness, limited real-time influences on microstructure across small regions. Then comes additive manufacturing, where processes, especially the processes based on laser, such as LPBF, which is laser powder bed fusion, or direct energy deposition, which is DED. These processes are dealing with very high energy lasers, very high energy electron beams that heat your metals very rapidly or your alloys very rapidly, and the temperature change happens within microseconds at the locations where the laser is shot at. Each new layer sees its own thermal cycling history, uh, coupled with the thermal cycling history of the previous layers, and the melt pool responds instantly. So, what is the effect of this? That the parts that are manufactured using 3D printing process are extremely high temperature responsive due to localized and dynamic energy inputs. Additive manufacturing has been almost a buzzword. Uh, doesn't come close to the buzzword of artificial intelligence, but it has been around for a decade or more now, and there's been a very clear and steady growth market size for this market when we see from 2017 to 2025, and only expected to grow non-linearly in the next 5 years. As is the case with many markets, the North American market alone shares 34% of the additive manufacturing industry. The parts that come out of AM processes are high performing parts made with high performing materials, and they offer very interesting mechanical and chemical properties, sometimes desirable but at times undesirable as well. There's a high strength to weight ratio, they are weather resistance. You can even use multiple biocompatible metals, that could be ideal choice for medical sector. So we have a few examples which are 3D printed, such as gear wheels, gear housing, heat exchanger for turbine engines, and such. Now the question is, we understood what metals are, what are the limitations of traditional forging methods. We understood what additive manufacturing is. Now the question is, and as the title of this talk is modeling before manufacturing, why do we need to model any of this at all? I mean, haven't we been doing this metal manufacturing or manufacturing for centuries? So what's new? Well, if you want to do additive manufacturing, then there is a lot of new things that we still don't understand. We do not understand. We cannot fully predict the behavior of a part that comes out of a 3D printer. And when we don't understand things, we often resort to experiments. So let's look at what sort of experiments are uh, are currently done. And this is a detailed list, but it's likely we may have missed a few tests here. So when we talk about aerospace, defense, or research grade additive manufacturing materials, in broadly speaking, there are four types of tests that we are looking at. We are looking at the part quality, we are looking at the mechanical property, we are looking at the microstructure behavior, and the last one is the build test. Within the part quality, there is density measurement. Within mechanical properties, there's tensile, hardness, fatigue, creep, fractography, residual stresses. So many of the students will identify with these tests. And when we start entering the domain of material science, which is microstructure tests, then we are looking at very expensive synchrotron, XRD, XRI tests, optical microscopy, BST, tomography tests, and other things. Now, if why do we want to do all of this? Because if we do the part quality test, we can understand what are the potential defects that we are going to see, or what are the defects that are already there, hidden in front of your part, inside your part. If you look at the mechanical properties, then we are talking about quality, the the quality of the product in terms of its strength, its service life, what could be the potential causes of failure, is there any distortion of the component possible. And when we look at material science or the microstructure side of things, then we are looking at melt pool dynamics to capture physics, phase and composition, microstructure information, and we can predict a lot of failures. And lastly, the first three set of tests do not qualify the part still unless the final build test or the part validation and benchmarking is done. Okay. Overall, these process parameters could be what is the uh, power of your laser, what is the scan strategy, what is the material that is using, what is the type of 3D printer, chamber conditions. There are probably 100 such variables that can induce defects in your 3D printed part. So process parameters induce defects in AM builds. Trials are very expensive and wastages cost in millions of dollars per year. Materials innovation and printability is a very long and tedious process. Today, if you want to try a new material or slightly change the composition of your existing alloy, it can take you years before you can deploy it into production. Aerospace certified tests are expensive and time consuming as well. Okay. So a little bit more on the material innovation and qualification. So in the previous slide, we looked at what experiments are needed, why they are needed, and how they help us. So one of the benefits of doing experiments is material innovation and qualification. Currently, we are printing, let's say 4, 5, 6, around 10 alloys, which are on the left hand side. There are some new alloys on the right hand side, another 10 which are under exploration. But what if we want to do tests for 500 new alloys? People and companies are making newer and newer products and requiring very specific alloy compositions. Okay, so if you were to go after qualifying each of these materials, you would be doing a bunch of these tests, and that can take a lot of time and a lot of money to be spent. I keep talking about that these tests are expensive, but let's look at what I mean by expensive. So traditionally, you could anywhere be spending 6 lakhs to 9 lakh rupees on validating a small part. If you were to simulate that part, if you were to reduce some burden of that experimentation, you could potentially be saving 65 to 70% of your cost. Okay, so for example, over the next 5 years, if you were planning to spend probably 5 crore rupees on material innovation, on process parameter optimization, using your metal 3D printer, then you can potentially reduce up to 3 crores from that budget just by incorporating modeling and simulation in your workflow. This benefit becomes even more acute when you're going after aerospace, biomedical, and defense grade materials. But even for non sensitive application areas, you will still see the benefits. And simulation and modeling, because it's a software based approach, it's a pure virtual computer based approach. The cost of simulation and modeling gets amortized over multiple research projects, over multiple engineering projects. Right? Let's see if this map opens up. Right. So this is basically a tree showing, overall cost for each of the tests. For example, if you were to do synchrotron XRD, it will take, 1 lakh to 2 lakh rupees for a test. With simulation, you can reduce it to 20,000 to 50,000, which is 70% or 80% reduction in price. Similarly, if you were to do traditional, like I said, so if you were to, for example, let's look at X-ray test, 40,000 to 70,000 rupees, but with simulation you can get away with 15,000. and so on. I'm not saying you can totally eliminate the cost, but you can definitely minimize the number of experiments that you are doing. Okay. Okay. So we have justified that modeling and simulation can be very fruitful for accelerating the pace of making metal 3D printing. A very general sort of used by all used by all sort of technique across multiple industries. um, some of the defects, I keep saying, we can minimize defects, we can predict defects, but what are the defects that we care about when we are talking about additive manufacturing industry? So when you look at a 3D printed part, you will see surface roughness. It could be in the form of humps, it could be in the forms of bubbles, keyholes, spattering, liquid breakup, keyhole porosity, vapor depression, vapor plume ejection. And for example, if you're following my pointer, you can see that there are some bubbles which are entrapped inside the metal. It is not desirable. If you look at this particular case, it's a deep keyhole, and just give me one moment. Sorry about that. Okay. Am I still audible?
Yes, sir.
Okay. Right. Like I mentioned, there are a lot of defects. I was talking about this deep depression. So laser is shot from top. This is a metal plate. You can see the depression has gone so deep, the vapor has gotten entrapped inside. Proper J-shaped keyhole formation here. And then, if you start looking at microstructure data, grain morphology, you can see those effects there as well. There could be pores, there could be keyholes again, there could be poor bonding effect between multiple layers, unmelted powder particles or partially melted powder particles. So this is a very, very complex and fine process, and it's very important to understand what is really happening in your process. Um, so when a additive manufacturing process engineer or a researcher sees a part, he doesn't want to see certain things. He doesn't want to see wastage of material, which is quite a lot at times. You don't desire uh, uh, you know poor grain morphology. You want good surface finish, and there are x number of things that you desire in a particular build part. And there is one aspect of 3D printing which can control all these defects, which is the melt pool geometry, melt pool shape, if you want to call it, or melt pool dynamics, wherein optimizing the process parameters, utilizing advanced monitoring techniques, employing machine learning for defect prediction and control, you can really get the desirable melt pool shape, uh, and consequently you can minimize the defects. Okay. to summarize, all this is currently done using experiments. Optimizing your melt pools, optimizing process parameters, material innovation, R&D. So we have established that all this is currently done using experiments. But if you were to really reduce the cost and accelerate the process of innovation in India, you can do that using modeling and simulation. Okay, so with that, I will now that I've made a case that yes, modeling and simulation is needed in this particular industry, let me jump to what I mean by modeling and simulation. So what you see on the left hand side is a real coupon, real 3D printed multi-layer thin wall. What you see on the second image is a high fidelity melt pool dynamic simulation. It's a multi-physics particle dynamics coupled with laser dynamics coupled simulation of a thin plate. Then you have a microstructure growth simulation where you can see thin, long columnar structures not desirable. And the last one is FEA based. So the first one is experiment, second one is CFD, third one is Monte Carlo, and the fourth one is FEA based stress and deformation simulations. Okay. Um, there are multiple processes in additive manufacturing industry. LPBF, which is laser powder bed fusion, WLAM, which is wire laser direct energy deposition, wire arc additive manufacturing. So first one is based on powder and laser, second one is based on wire and laser, and third one is based on electromagnetic forces and wire. Okay. So we are here. A lot of you come from the CFD background, so you might be curious to know what are the equations that are being solved in really, simulating these complex processes. So of course, we need our glorious Navier-Stokes equation. There could be some additional force terms. For example, in the case of electromagnetic forces, we have added additional force terms to the original momentum equation. uh, One critical and probably the most important piece of physics here is the multi-phase interface tracking. So we are using four-phase multi-phase system. Why we need four phases? So the solid metal, the molten metal, the vapor metal, because temperatures can easily exceed 3000 and 4000 Kelvin in these processes. And the last one is the ambient gas or the inert gas in which the entire 3D printer operates, or the chamber of the 3D printer operates, right? So we have four phases, and at all times we are tracking the interface between any of the two phases. We need temperature dependent properties. This is another critical piece because you're going all the way from 300 Kelvin to 5600 Kelvin. So your properties significantly change as the temperature changes. Surface tension forces, Marangoni convection, which is basically temperature dependent surface tension that causes your molten metal to accumulate one part of the domain and leave certain other parts of the domain. Okay, so that is on the CFD side. On the DEM side, we are using a lot of particle modeling where we create the powder beds. Uh, and then there's a lot of defects that we were talking about. We are talking about keyholes. If you notice this particular animation, this is my favorite one. You can see a laser being shot at a metal, and just notice the fidelity and the capturing of a huge air bubble inside this melt pool, and some spattering is also visible. Okay, so the air bubble will be entrapped. Yes, there it is. Okay. Then these days people are trying to work with new shapes of lasers, which is I believe we do not have any laser beam shaping facilities in India. But that doesn't mean we can do research on that. In fact, researchers from a few IITs are already working on this, and they are very interested in understanding the impact of, for example, a ring shaped laser beam on the microstructure of the metal. And for that purpose, simulations can be used because you actually don't have a ring shaped laser beam. Okay. Then you want to understand the thermal cycling plots based on the fluid interaction. You want to understand spattering and such things. Okay, so that was all CFD. Now moving on to the next part, which is the microstructure evolution, because we don't want to solve just CFD, and because that is not really the complete story when it comes to additive manufacturing. We are talking about Monte Carlo methods. We are talking about crystallographic plots, and the main focus here is this is the type of data that you would get from tomography, tomography experiments that I mentioned earlier. But what you have here is actually coming out from simulations, very detailed slice by slice, time dependent microstructure evolution at different parts in your metal block, as the laser melts and solidifies it. And what you have on the bottom right is one of the relatively new developments at Pandav, where we take the entire CFD melt pool dynamics data, and we try to uh, capture the exact melt pool from CFD, and we simulate microstructures inside that melt pool only. Rather than assuming a perfect hemispherical shape of a melt pool, we actually take the real melt pool shape and the temperature history from the CFD data. Okay, so how does it look in coupling with each other? Melt pool dynamics, which is CFD, when coupled with microstructure, which is Monte Carlo. So you see on the left hand side, the blue color on top is the vapor, and you can see how the melt pool is dynamically changing, and as it solidifies, you can see the microstructure evolution as well. You can even see a single, spot of yeah, some of the vapor is also entrapped here. How does it look in comparison to the experiments? I mean, it's quite well actually, compares quite well. So if you see some of the part of the vapor was probably entrapped here, either that or the experiment failed to measure the microstructure data here. It is one of those things. Either way, this is what we are simulating from simulations, and you can see very nice microstructure data. You can even see a bubble entrapped here, and then in the previous simulation, you can observe one of the bubbles which is formed here. Here it is, and then it flows to the bottom top. Okay. So the end-to-end simulation for additive manufacturing, powder to part scale is our goal, and cutting down the cost by 67% in the initial process optimization phase itself. Now, some of you may wonder, you are really not, covering the entire pipeline, because the additive manufacturing doesn't start where you already have powder, you already have some metal with you. It actually starts at the powder manufacturing state itself. In fact, for that, we are already working on gas atomizers, supersonic gas atomizers, where powder is actually manufactured with accurate sphericity being captured. We take that powder, prepare powder bed using discrete element method or particle dynamics. We take that data, shoot laser at it using CFD plus Lagrangian laser dynamics approach. We take that data, put it into microstructure to capture the grain morphology, grain microstructure, take that data and we put it into part scale FEM. Okay. We'll look at the three case studies here. Different sorts of laser parameters and we'll see how the results change. In the first case, we are looking at pure aluminium laser being shot at it. In the second case, we are looking at ALSI 10 mg, heavily used in defense these days. We are looking at the LPBF process for that. And in the third case, we will look at a multi-material, which is aluminium and copper multi-material building or welding, if you want to call it. Okay, so let's start with the pure aluminium 3D printing. Left side we have the experimental video, right hand side we have the simulation video, and you can, if you observe carefully, you can appreciate the fidelity at which not just the vapor is captured, but each and every pore is captured as well. Okay. In this case, people are very interested in understanding what is the front angle of the melt pool, because that apparently decides the microstructure as well. So in the experiments, they were getting around 85 degree as the front wall of the melt pool, and we were getting around 85, 82, 81 when taken at different sections. Once again, this is the top view. Okay. And right hand side is experiment, left hand side is simulation. A lot of pores uh, are entrapped and left behind permanently in the part, which is quite bad. Okay, second case is ALSI 10 mg, where we are looking at uh, depth and width of the melt pool, and we are getting in width we are getting deviation of 5 to 20%, in depth from 3 to in some cases up to 40% depth variation is also there. Now this material is very is heavily under research right now because of its high printability, balanced mechanical and thermal properties. It is lightweight. It is easy to post process, compatible with post processing, and already has a good track record in aerospace and defense, or about to have a good utility. Thermal and corrosion resistant, it can be tailored for microstructure, desired microstructural properties as well. Okay. So some of the defects that were not visible earlier could be seen here. You have some pores, you have a depression here, some defects at the end of the build, and this is not desirable. Some of the structural defects that we can see here in terms of microstructures, and again we are comparing the simulation data with experimental data. The trends match well, except for a few exceptions, and of course this can be improvised even further. The third one is quite interesting: aluminum and copper multi-material welding, where used in battery systems. It is used in electric vehicles and aerospace, where aluminum carbon fiber composites are made. Biomedical, where metal and ceramic interfaces are made, and in additive manufacturing for sure. Okay. So just look at the fusion zone. On top you have aluminum, bottom you have copper, and you can see a nice fusion zone and a weld crater, sort of a dune formation as well. Okay. Moving on to the next scale, which is a part scale modeling. We have actively started working on closing the cycle of capturing many scales. So the largest being the part scale, where people are mostly interested in deformations, in thermal and thermomechanical stresses, and the orientation at which you build a certain part in 3D printing can give you very different results in terms of stress management, thermal stress management, in terms of distortion minimization. Okay. Okay, so how does this all connect to open source? FOSSEE is all about open source, and not even once have I mentioned that this is open source. Open source is free of cost, as Mrs. Payal mentioned earlier. But there's another huge advantage of using open source frameworks, which is, for a country like India, which is still in its initial stages of development, this gives power in the hands of users, in the hands of students, professors, and researchers to take the fundamental equations and build and apply them to their particular needs. So in our case, we took a huge gamut of open source libraries, all the way from OpenFOAM, Lights, uh, many of the AI-based TensorFlow, GPU-based libraries, uh, and, and and other libraries as well. We took them all, and we found that at the end of the day, it's the same fundamental equations that are going inside ANSYS or AM Prava. But then, what's stopping us from creating softwares like ANSYS in India? It's our it's our resistance or hesitation in using open source frameworks. So what we did, we took all these libraries. We realized that they are great libraries, but unfortunately, they are also limited in some capacities in terms of what the industry application wants. We basically coded our own equations, we added our own codes, modified the libraries, corrected their bugs, added a user interface, parallelized the libraries, and we did entire process development of that a software should go through, and we created AMPrava out of it. So open source is not only good for just saving the cost and learning, it is actually good for accelerating the pace of innovation for any country. So I would urge all the students, especially and many of the professors, to stay connected with FOSSEE. Contact us if you want at any time, and get your fundamentals straight. And the only way to learn good fundamentals of CFD is by learning open source. And OpenFOAM is one of those great pieces of software, or I wouldn't call it a software. It's a bunch of libraries to get started. Okay. So a little bit about Pandav applications. We are located in Bareilly, Uttar Pradesh. We provide computational engineering simulation software development services across multiple industries. Today, I talked only about additive manufacturing, but we do a lot of work for data centers, for mining, metallurgy, um, food industries, automotive, aerospace, defense, and you name it. I mean, basically, truly industry agnostic. Okay, so thank you very much again for having me, and I will be happy to take any questions.
Any questions for Mr. Advait are welcome from all the participants.
So there's one question in the chat by Mr. Arvind. He's asking, I have a question to Professor Advait. You mentioned by experimenting via simulation also have its cons, considering the minimal cost expenditure when compared to experimenting via XCM or XRD, etc. Could you elaborate on it? That is the question.
I don't see it in the chat, but
1 minute, I'll copy it and paste it.
you mentioned by experimenting via simulation also have its cons, considering them. Yes, I mean simulations. It's a cost on electricity, it's a cost on computers, it's a cost on manpower. So even if you go ahead with a completely free simulation software, I mean, there's always a cost associated with everything, but that cost is significantly lower when compared to the experimental cost. Because if an experiment such as synchrotron and an XRT experiment goes wrong, there's a huge cost associated with it. But when a simulation goes wrong, you can just crash your simulation and restart it. However, I mean, I'm just saying that the costs are significantly different for the two. Material properties are very important in these types of simulations. How to get accurate set of. Yeah, so this is a great question, and material properties are around 10 to 15 material properties we have accurately captured, not by experimentation, we'll be very honest, but by a lot of good work done by research labs all over the world, and as reported in the research papers as well. Uh, but when it comes to new alloy properties or super alloy properties, this is something that needs to be gathered in a careful manner. We don't work on that side of things, so I have limited comments on that. But so far 99% of the alloys that people are considering are already being modeled and simulated. Follow-up question, but how are the performance and output compared to experimental? Like I said, I mean, it depends. The more accurate you set up the simulation, the more accurately you provide the material properties, you can get into the realm of 90+% accuracy with simulations compared to experiments. But if you want to run on coarser meshes, if you want to make more approximations, then your accuracy starts dropping and it can go down up to 70-60% as well. High temperature responsiveness for also, what do you think is the biggest challenge for industry absorption for AM, obviously, other than high cost of R&D? Well, I mean, AM parts inherently go through a huge temperature range. You start with a preheated 500 Kelvin plate, and then your powder is basically, 350 Kelvin powder, and then you start heating them, take it up all the way up to 5,000, 6,000 Kelvin in some cases, cool it back down. So your basically your metal has seen a huge and aggressive temperature changes already. So later, when it is thrown at real operational conditions where your temperatures are changing very fast, in those cases AM parts are likely to be more robust in their operation. What is the biggest challenge for AM? I feel the biggest challenge is the slowness in terms of research, in terms of completely understanding the materials and their response to the process parameters as well. Could you also please computational? Yes. So computational time, as we all come from this domain, we know the same simulation can take 15 minutes and it can also take 15 days. And that is the case with most of the simulations in this presentation. Most of them are a few hours long simulations, but then we have run simulations that have run through for 7 days to 14 days. The very similar simulations. So depends on what you want. You're fine with 70% accuracy. That's okay. If you want to go up to defense sort of activities, then maybe even 95% is not enough. If accurate material property, what is the other way for consideration? If material properties are not available, then you have started approximating already. And up to my best knowledge, you can use some empirical approaches in estimating those material properties. CalFat gives you some of them, but then at the end of the day, if you don't know material properties well, you will see the effects of that in the overall accuracy of the simulation. Can we use open for combustion simulations? I Yeah, I mean, you can. I think other people will also comment on that. How are the CFD results validated in the cases here? Oh, they are validated with the real experimental data collected from the research labs, from our actual users. So we have around 10 research users all over the world right now, and they are, you know, trying to validate our results. Reason behind after CFD analysis also failure of components. Well, because it's very new. In if you were in or aerospace industry, you wouldn't say this because there's a huge trust on CFD simulations. But when it comes to additive manufacturing, it's a relatively newer industry, and hence there is not much. So start with, there's not much CFD analysis happening in additive manufacturing industry. When sufficient analysis starts happening, I think the scenario will change. I've installed OpenFOAM, but I'm not sure whether it is correct as I could not open Bits Daily directly. I would,
You
I
can
would,
skip this question. I think I would request you to contact in our FOSSEE email and we will guide you through.
sure. How DEM, CFD, and microstructure in terms of we do not couple them at the equation level. We couple them in terms of data transfer. We take data from DEM, put it on CFD. We take data from CFD, put it on micro level. Because if we couple everything and make a huge matrix which is out of control, it will become a good research project but never be useful for the actual user. Okay, I will skip the open form questions. I think there are better people in the audience to answer that. Any further questions?
I wanted to raise a few, and maybe your experience will help the audience in that case. So basically, as you know, the vision of this workshop is just, we have so many new users of OpenFOAM or students particularly who would want to get motivated to cross the steep learning curve of OpenFOAM, and that's where we want to basically show them what is the real life application of OpenFOAM. As you said, it's not only for research project, just for writing papers, but also for actual real life applications, and it can really reduce the cost of these commercial licenses and help SMEs, smaller businesses to come forward and do their business. So what, and I think we had this discussion personally before, but I want to make it in a public forum just again. So while building this startup based on the open source tools and modifying them and everything, but when you actually present them to um, uh, your clients or whoever wants to take this tool and use in real life application, what do you feel about the challenge in the mindset in terms of scaling up the workforce and training the workforce in the industrial scale?
One challenge that we face is people asking us, because they are already using ANSYS or some other software, so they will have to learn a new piece of software, and that is a fair question, I would say. But that's the nature of it. If we can show them that, look, this is a new software which not only uh, exceeds the capabilities in certain areas. I wouldn't say we compete with ANSYS or anything, but in certain areas we are better. If you can show that, and if you can also spend time from your side in skilling up their workforce, I think they're very open to adopting any software for that matter. Also, it depends on the country. When we pitch this software to American audience, and we tell them that, look, the engine in the background is a bunch of open source libraries, they get very excited about it,
Yeah.
because they have heard the names, they have probably used it in their academics. The situation is different when it comes to India and similar countries, where when we say that the backend engines are actually open source libraries, then there's some resistance there. But I think it's changing with time. 5 years ago, it was almost impossible to convince anyone that anything can be done in open form in real world. But today they are paying us to do that. So I think things are changing very fast now.
Yeah, I mean, towards that, that was exactly my next following question. That what is your verification and validation strategy from your company to convince your clients that yeah, OpenFOAM can do, not only can do real life simulations, but also can do with the same level of same order of accuracy as the commercial codes? Because there are some myths that if if the users pay for the licenses, the simulations are more accurate. And this is not only in India, it is worldwide. So how do you overcome that, and what's your particular strategy for verification and validation?
Right. Verification is something that can be done from our internal coding point of view, but validation is something that is more inclusive. And we do collaborate with universities, with research labs. We ask them, you give us our data, let us compare our simulation data with your experiments, and if it matches well, I think, I mean, even they build trust. And most of the customers, they do not just right away take our product. They, of course, want to make sure that at least for a few cases, the results are matching their experiments. So that is something that is some extra effort that we have to put from our side as of now.
Right. And I was actually very curious in terms of, like, you have partially answered that. So, for example, in aerospace industry, which I am mostly involved in, the real life applications or industries, they are very concerned about the turnaround time rather than accuracy. For example, of course, most of the aerospace industry uses URANs instead of LES or DNS, because we cannot really afford to do that in industry scale. Or in most of the scale, we also industries also depend on model order reduction, some reduced order models, just to get the back of the envelope calculation, which with some factor of safety would suffice for their design and will always be on the safer side. So we really don't want to know that minute underlying physics for industry purpose. So I was basically more or less curious on additive manufacturing side, what's the mindset in the industry? Would they really want to go for that scale resolving simulation, or they are happy with coarse mass, I mean, more or less accurate simulation where the results are within the same ballpark? Or do you have also provisions for model order reduction? Do you think these high fidelity simulations can lead to some reduced order models which can be better used in the industry scale?
Right, it's a mix of both actually. People who are into pure research, I mean, uh, they of course want high fidelity simulations, but industry users where the turnaround times, like you mentioned, have to be very quick. There, they don't care what we are using in the backend; they just care about the results. So for that matter, we have started developing. I wouldn't say low order. I would say low dimension models instead of 3D, some approximations onto 2D, and then some all the way up to 1D. In fact, we have developed something for a company. It's an electron beam 3D printing company based in Europe, and I mean, we are currently doing 2,400 layers of simulations under 20 minutes, which if you do with CFD, it will take years. So, of course, if there is a requirement, then we care about solving the problem and not just enforcing, forcing high fidelity simulations down their throat. That's not our goal. But it's a mix of both. There are people who are not happy with these equations. They say, there's just something missing here, something you add this. So we are open to everything. Whatever their requirement is, we develop accordingly.
All right. I think for the sake of time, we can keep discussing and I will lose track of time. So I'll just hand over this to Ismail and Ivan and whoever are coordinating this. Thanks, Advait. So I wanted to just thank you on behalf of the FOSSEE team for your time and sharing your knowledge and your real life experience of building the startup. And I think it's contributing significantly in the additive manufacturing side in the India, and I keep following. So thank you very much, and we really appreciate your experience sharing with all the particularly new engineers who would like to use OpenFOAM and for real life applications. Thank you very much.
Thank you, Dr. Bose, and it's nice to see you again. These are
Sure.
the platforms that gives us the opportunity to meet again.
Sure. All right. Thank you.
Yeah,
Yeah,
thank you
Ivan,
so much,
over to you.
Mr. Advait. So I think this session was really very, very helpful for the students who are now, studying in colleges and they're aspiring to join the CFD industry, because they got a very, deep insight about whatever Mr. Advait is working on now. And yeah, thanks a lot. Thanks a lot for joining. And if you have any more questions for Mr. Advait, we can take up the relevant questions, and you can email us at the end of the workshop. We'll be sharing our email ID. And then if we receive any relevant questions, that can definitely be answered by Mr. Advait, and we will coordinate it. Okay. So yeah. So Professor Chandan, would you like to interact with the participants before we go ahead with the hands-on session?
Sure.
Or
I can just address them for very briefly.
actually, I briefly introduced you before you joined.
Yeah.
So,
Sure.
so let me do it once again. So, Professor Chandan Bose is a faculty member at the University of Birmingham, and he's also a visiting faculty at IIT Bombay. So, he is leading the team as a PI of the CFD team of FOSSEE, and we are really very thankful to him for leading this team. And he is the one who is showing what we are supposed to do in the FOSSEE project in the CFD team. So thanks a lot, Professor Chandan, as always, and once again. And over to you.
Thank you. Thanks, Vailji, for the kind introduction. I think it's more than what I deserve. But yeah, so coming to the point, I just wanted to come up and thank all of you, all the attendees, for making this event successful. And we were planning for this industry academia interaction kind of thing for a long time, and ultimately it's slowly getting momentum, and we have fantastic industrial partners from different sectors, and we again thank all of them to agree to spend their time for this event and share their very important real life experience on using open source tools such as OpenFOAM for their industrial problems or for solving challenging real life problems. And so basically, I would just like to say that the vision of this workshop came from the idea that we every year train many new engineering students as per the vision of the FOSSEE project on open source tools and softwares, and particularly our team is focused on promoting these code which is called OpenFOAM. Again, I don't call it software because it is nothing but open source libraries which is written in C++ language and which follows a particular finite volume method approach of CFD. And it's developed by many researchers, ideally the pioneer contribution coming from Professor Hab Jessup, who is a professor of Cambridge now, and Professor Henry Weller. But ultimately, it has become a community code where the community of OpenFOAM contributes. Although it has gone up to different changes from for different commercialization attempts, and but it still remains, at least some of the fork remains for dedicated for open source contribution, and which is open to community to contribute and develop based on the ideal um, application for their problem, and based on building on the soldier of the giants based on the actual repository of the main Navier-Stokes solver and other structural solver which are written in finite volume method. So the primary objective of this workshop, I would say, is to give you examples of the best applications of this code library, or which some people would might also can call it yeah, I mean it, I would better call it library because it's just bunch of code. So um, in different sectors, and particularly our focus is on India, and to show that even within India, how can we use these open source codes to develop our R&D sectors in different industrial applications, such as I think you have already have listened to Mr. Advait, who is working on the manufacturing side, but he has many other areas. But one of the things that he highlighted, how can we use this um, open form code to build on more user friendly user interfaces and adding more models, more equations, and make it ready for real life industrial application. But I just want to also highlight what are the upcoming areas our industrial partners will talk about. Starting from manufacturing, we have next, we will talk about droplet dynamics and different machine learning based models will show you or demonstrate the application of OpenFOAM in the water sector, in the combustion simulation for diesel engine, etc. And also, we have partners from growing CFD startups, where our industrial partners will basically show you how to make meshes and how to optimize the CAD models for different industrial application. And then we in the other days we actually have other applications such as renewable energy. Will We actually have HVAC applications, and we have marine applications, and so on and so forth. So I think it's not everything. It's not exhaustive, but I think it's a good collection of application to show you how you can use these open source codes for different industrial sectors. And it will also give you an example where after graduating from your engineering degree, and if you make yourself an expert of developing this open source code, who will be the possible recruiters and where you can get your job. So ultimately, the other aim of this workshop is to show that what are the possible employability sectors in India where you can secure a high profile job by showing your skills in open source codes such as OpenFOAM. And I hope that it will be useful. We have also planned with our research assistants to demonstrate to you one of the case studies that our students have done in previous years, and to highlight how those case studies done by our previous students can be extended towards this kind of application. So those will be very much complementary to the expert talks given by our industrial partners. So I strongly encourage all of you to keep connected and see the demonstration and try to imagine how you can take such a case study from the huge collection of case studies supported by FOSSEE, and then build your portfolio towards your industrial project. So as you all know that this is very much a culture in the software community that when you ask for job or when you apply for a job, your CV should reflect a long list of portfolios of your experience of developing codes and contributing to such problems. So in the CFD community, it is also very useful when you ask for job, when you graduate, particularly I'm talking towards undergraduate students, that when you want to get employed in the CFD industries, if you have a long list of portfolios showing your skill that I can use, I can develop and modify this open source code towards real life applications, and these are the industrial projects that I have carried out, will immensely help you to stand out in the very competitive scenario. So I hope this workshop will give you some idea towards that, and maybe also give you the contacts of such industries where you can do internship, build your profile, and so on and so forth. So starting from manufacturing to water sector to renewable energy, we tried to cover a large arena of industrial areas where we see the application of this open source code. And I just wish you all the best for towards a very enriching 3-4 days of workshop. And I would like to thank all the team members of the FOSSEE, including Ms. Pyle, for managing the project very efficiently, and all our research assistants who have spent their tireless time to plan for this workshop. And I'm very happy to see the enthusiasm that has come out of the workshop. I can see now 220 plus attendees, which I would say that is very satisfying for us to organize this workshop. And I just would like to encourage you to keep connected towards the end of this workshop, and hopefully it will be a very, very good learning experience for all of you. Thank you all. Yeah, I hand it over to the organizers now.
Yes. So thanks a lot, Professor Chandan. So yes, definitely now it's a time to move ahead with the hands-on session, and our team member Evan Fernandez is here. And the most important part about this session is all the case studies which will be which our team members will be demonstrating in this during this workshop are done by students like you all. Okay, so students who volunteer by themselves, they can actually complete and submit a case study. They can also enroll themselves in our internship and fellowship programs. Definitely, we have a screening task and we have a selection process. But the students who join in our programs, these case studies are submitted by them. It is not that our FOSSEE team members have completed them. So it's a very unique part of the FOSSEE project that we train the learners and enable them so that they are capable of producing an output by the knowledge that they have acquired. Okay, so over to you, Evan. You can start the hands-on session.
Yes, ma'am. Thank you, ma'am. I'll share my screen. Is my screen visible?
Yes.
Thank you. Okay. So welcome to the Industry Readiness Workshop, CFD Open Forum. Before we begin with the hands-on session, I would like to give a brief overview of how OpenFOAM case setup is set up. So most of you are beginners. For those of you who know already, it is really irrelevant. But for people who are really starting off with OpenFOAM, this is a good experience to understand how you set up a case in OpenFOAM. I'll be very brief with it. So this is your ideal case structure that you would have in OpenFOAM. You have three main folders. Okay. So you will have a zero, constant, and system folder. Now your zero folder, this is where you will be setting all your initial boundary conditions. So this can be your velocity, pressure, temperature, and in our case, we have some additional parameters as well for the demonstration. And next we have our constant folder. This is where you would save all the parameters that remain constant. Like if you are running an incompressible solver, then you would have your density remaining constant. You would specify your velocity, not velocity, but the fluid properties that you are giving. And some of you had asked Mr. Advait about where do you type in your properties and how are you getting your physical properties of your alloys and the material that is using. So this is where you would be specifying all your properties within constant folder. And lastly, you have your system folder. This is where you would have your meshing parameters. You would have your control parameters, that is your start time, end time, your delta T, that is your time step. And you would have your schemes and solutions. So those are your discretization schemes and any parameters like relaxation parameters and all that you require to tweak. Those are where you will be changing your things. Okay. So the very first thing, let me open the browser. So for a case, we will be downloading a case study that has already been published on our website. So if you go to, sorry, you go to completed case studies. Within that, you have a case study known as calculation of reaction-based residence time. Okay. It is done by an intern from a summer fellowship. So you can download this case. I already have it downloaded. So I'll show you why. Okay. So what this case is exactly doing is we have a pipe and we are going to be modifying a solver, that is your scalar transport form, to better understand or to simulate how a scalar moves in your domain. Okay. So by scalar, what I mean is, let's switch back to the PPT. Okay. So by scalar, what we mean is like a scalar as a whole is a quantity that is transported in your domain without disturbing the flow. Okay, so you can think of it as like if you have a flow and in that you're introducing ink, like an ink jet. So that ink jet is not going to be manipulating or disturbing the flow that you've already set. So you're first initializing your flow and then you're introducing an external parameter and you just want to see how that external parameter is going to be transported in your domain from point A to point B. So for this very reason, you would have to first solve the continuity of flow equation, that your Navier-Stokes equations. So for that, you would have your continuity equation and your momentum equation. So these are the equations that we have. Additionally, since we are using the scalar transport form, that particular solver solves your energy equation. So you would have your solver solving the energy equation as well. Now in our particular demonstration, we are solving for the flow as well as the energy equation. And then we're taking those values or the end product of what we're getting from the simulations, and we're transferring that into a new solver that is custom made to find out the scalar transport or the scalar properties that we will be introducing separately. So in this energy equation, we have alpha on the right hand side, alpha and all the parameters. So your alpha is your thermal diffusivity, and you have K and then rho Cp. K is your thermal conductivity and Cp is your specific heat at constant pressure. So all these parameters will be essential when you are creating your solver. Okay, so keep in mind all these equations that you have, because if you want to develop a solver, you need to know the underlying physics that is going on. Only then can you better understand how and where to make the changes. So once we are done with the energy equation, this is the scalar equation that we have that we will be introducing in the new solver. Don't worry, I will show it step by step how is this process done. So you don't need to get overwhelmed by just seeing the equations. So for the scalar equation, we have our main scalar equation that is on the top over here. Now on the right hand side, we have the diffusion term and the reaction term. So for our case, we are keeping diffusion as 0 to simplify the whole equation. In your case, if you want, later on, you can tweak the parameters, you can increase diffusion and see how it affects your whole simulation. But for our case, we're just going to keep it simple. We have 1 hour, so we just try to push everything within that. So we have diffusion, which is set to 0. So obviously this term is going to become 0. And for our reaction term, we have basically changed the equation. So based on your reaction, it is a irreversible reaction. So you have like your reaction going from A to B, where A is your reactant and B is your product. So in that sense, we have the term on the right-hand side, ASE. Now this particular term, we are going to be solving using RNS equation. So again, this equation will be put in your C file or your solver modified set files. So in this, A is your pre-exponential factor, E is your activation energy, T is your local temperature, and R is your universal gas function. Now in this entire equation, you have most of the parameters that are set to constant, only T being your variable parameter. So your local temperature is what you will be getting from your flow equations, okay? That is the reason we are solving for the velocity, pressure, and temperature. So we are first going to solve those equations, then come back to these equations and input those values within this. So these were the equations. Now coming to the solver itself. Okay, so let's first start with the case. So suppose you download the case, you have, this will be your case. Once you extract everything, you will have these files. So you can open the case files. Now within this, you have the report. You can open the report and you can read this because all of the equations and where the changes are made are specified within this report. It's well detailed, so it's good. You can read this and can go through this. So once you open your folder, you must first go to the solver setup. There is a README file as well. You can open this as well. So let's open this. So in your README file, these are the basic instructions of how to compile the solver, how to run the solver, and any changes that are required. All of these are mentioned in the README files as well. So it's always beneficial to first read all of these files and then start doing something. Otherwise, you might end up doing something and you don't know what is wrong exactly in the whole setup. So once you read the README file, you can open the solver setup. So in the solver setup, you have this new scalar transport form. Okay. So you can open this and you have a create field modified and you have the new scalar transport form. That is your basic C file. Okay. And along with that, you have a make folder. Within make, you have files and options. Okay. So I've opened these files. So on the left, we have the modified files. And on the right-hand side, we have our original scalar transport form files. So
Ivan, can you increase the font size?
Okay, just give me a minute. Is it better now?
Yes, yes.
Yes.
Okay, thank you. So on the right-hand side, we have our original files, your scalar transport form.c file. This one. And on the left-hand side, we have the modified files. Okay. Now, where can you find these original files? Because you have to obviously copy some of these and then modify them to make your own solver. So in your file structure, when you go, so suppose I open Ubuntu, okay? So once you've entered your Linux environment, it's at the bottom here. So you have Ubuntu 2204. Now, since we're using OpenFOAM 9, your folders are always saved in your OPT and under OpenFOAM 9. Okay. Under OpenFOAM 9, usually we go to tutorials to copy some tutorials, but in this case, we want to go to applications. Within applications, we have solvers. And now over here, under basic solvers, we have scalar transport form. So you can see over here, we have the scalar transport form C file, then we have the create fields, that's a header file. And then you have again, these additional make files in which you have the files and options. These are where you will specify your libraries and where you want to save your solver and all those parts. So once you open this file, we first go with what is in the make folder. So in your make folder, you would have options and you would have files. Same goes for this one. Okay, options and files. Now, the very first thing you would notice is whenever you are modifying a solver, the very first thing you do is always change this path, that is foam user app bin. So originally you will have it as foam app bin. You should always change it to user app bin. What this does is that in case you are making a new solver, like if I were making scalar transport form and say I save it as scalar transport form, how will OpenFOAM or the whole Linux environment differentiate between which scalar form you're trying to, which scalar transport form you're trying to enable? So for this very reason, we make a user-defined app bin. So what this does is it will store all your custom solvers within this user bin. Okay. So if you create something that is wrong or you cannot change it back, it is at least saved in a user bin and it is not affecting your original files that you have for OpenFOAM. So that's why first thing you do is change the username. Basically, you change this path and you put user before app bin, and then you can add your custom name. So now in this case, the intern, he thought of writing new scalar transport form modified solver again. So in this case, we have the scalar transport form. Once you're done with the files, you can save this. Then you move to the options folder. Okay. Now in the options folder, most of the times there isn't much of a difference because you're using the same libraries, provided you are trying to modify something on that base level. Now, if you're modifying something to an extreme level, you would change some of the libraries because you would have to introduce some libraries and anything that you are trying to introduce in your solver itself. So these are some of the things. Now, if you're changing versions, usually whenever you're changing from say OpenFOAM 9 to OpenFOAM 12 or something, some of these paths are a bit different. So again, depending on the version you are on, just check these paths because sometimes in the newer version, they have tried to summarize everything within one folder, whereas in the older version, it was segregated into multiple folders. So you can always check these. But ideally, you would have no problem running this on OpenFOAM 9. Okay. And the user even mentions that these particular files are created specifically for OpenFOAM 9. So if you are trying to run it on another version, you would have to check the compatibility. Okay. So once you have made some changes in your options folder, you can go to the .c file. Okay. So now in your .c file, on the right hand side, we have the clean one, and on the left hand side, we have the modified one. So the very first thing you would do is you have this particular block, okay? Include block. So this is where you are calling all the header files that you have. Like if you know basic C++ coding, C++ coding, you would have to call some headers if you don't want to cluster up the whole C code. So you would have a header file and you would have the .c file. So in your header files, it's usually where you specify any of the important parameters you want. And then in your .c file, you just call those header files. So that is what is happening over here. We have the CFD header files, FE models, FE constraints, simple control. So all of these are the header files, but in our modified case, we've just mentioned an additional file called as dimensioned constraints fold header file. What this does is it will just give us can say liberty to modify some things in your constant folders or in any of the constant parameters. Additionally, if you scroll down, you have again some more header files. And over here, we have something as the create fields header file. Okay. Now, if you noticed over here, we have that create fields. This is where you would specify all the parameters that will go in yours. Like if you want, you can add your transport parameters. Like in our case, in the PPT, if you remember, we want to introduce these additional parameters as a constant. Okay. So in the transport properties, we will have to introduce these parameters. So those are where you will be mentioning over in your create fields, you will be mentioning all these parameters. Okay. So before we go more deep into the C file, let's first see the header files. Okay. So in our header file, in the original case, we have a header file for temperature and we have for velocity, okay, because it's solving these two equations. But in our case, we want to introduce a scalar. Okay, so this scalar, we'll be naming it as scalar 1 and a scalar 2. So we have two scalars. And additionally, you can add some more scalars, like if you have 4 or 5, just as Mr. Advait said, in case you have multiple, like he has been solving for 4-phase. So anytime you want to introduce any new parameter or any new material, you can do that within this create fields modified H, within your create fields header file. Okay. And then you have to specify the same in your .c file. So these are just the header files. You have to mention that in your C files for it to properly function. So first we are mentioning a scalar 1 and scalar 2. Okay. We are specifying some basic parameters that it should be like runtime, it should run with the whole simulation and all those stuff. Must read, auto write and all. So those are the basic parameters. As we move forward, you have the U, that is your velocity. So that is the same as the one that is in the original file. And we also have T, but since we are solving for Arrhenius equation, we have clubbed that all together. So you'll see that in a minute. Then once you are done with specifying, now all these files that are before transport, these are which will go in your 0 folder, okay, your initial boundary conditions. So if you were to open a scalar transport file, so in the file that we have, the demonstration file, we have the solver setup, and also we have some laminar case. Okay. So I'll show you the flow file. In this, we have used for temperature a scalar transport form. So if you opened this, you would have primarily in a scalar transport form folder, you would have T and U. Okay. Because we're solving for only these two equations, whereas in a flow case, at least for simple form, you would only have velocity and pressure. Simple form algorithm does not solve for temperature. So those parameters you have to introduce in your new solver. Okay. So this is where you're doing this. You're introducing some parameters. So the next time you compile this solver, you will, if you don't specify any of these parameters like scalar 1, scalar 2, in your 0 folder, it will prompt an error and saying that these files are not introduced or are not mentioned in your 0 folder. Okay. So once your 0 folder is set up, all your parameters that you want to set within that is set up, we move to the transport properties. Now here is where we are going to be introducing all those parameters like Arrhenius equation, any of the equation that we're using in the energy equation. As I said, for alpha, you would require to define your thermal diffusivity, thermal conductivity, and your specific heat constant. So all those parameters have to be introduced. So this is where you will be introducing all of those in your transport properties. Okay, I'll show you side by side the original files in transport properties once we've done compiling this, as well as the files that are modified. So in your transport properties, this particular block is just reading your transport properties file, and then down. Now in your original scalar transport form, you have the diffusivity. Okay. Now here they are diffusing the temperature. So you have diffusivity with respect to temperature. That's why it's set to dT. But in our case, we want to specify the diffusivity on the scalar. So that's why we have a diffusivity for scalar 1, ds1, and we have the diffusivity for scalar 2, ds2. So these two we have defined. Along with that, we have Arrhenius equation. So the temperature block, we've just copied it from top to down. And here we will be specifying the Arrhenius coefficients. So over here, as I mentioned, for the energy equation alpha, you have rho, you have Cp, you have kappa, that is your thermal diffusivity. Sorry, you have, this is your thermal conductivity kappa, and thermal diffusivity is your alpha. And along with this, we have defined a Ks block. Okay, so now this Ks is just your, as I said, the left-hand side in this equation, Ks, we want Ks to solve this equation. So we've defined a block named Ks. And within that, we have specified A, E, A, R, all of these parameters that were in Arrhenius equation. And these particular equations will be constant. That's why they will be set in your transport property under the constant directory. So they will remain constant throughout the equation. And anything addition to that, it will be solved using the whole simulation. Okay. So as I said, so you are specifying that Ks block. So this is where you would specify the Ks, and then you have the additional parameters, that is your create phi, create a free model, and condition. These are some basic header files that you require for OpenFOAM to understand and to simulate your whole simulation. So this is your header files, okay, both of these. Now, once you have introduced those header files, you can go back to your C file. So the very beginning, you have the simple loop, okay? So while your simulation is running, everything within this, what you want to solve while your simulation is running will come within your while loop, okay? Now in C, C++, you will know that you have to specify things and how does a while loop work. So I'm not going to explain how does a while loop and all those things work. But whenever you want to solve something within that equation time or the simulation time, you specify it within your while loop. So while your simple algorithm or your simple loop is running, you want to solve for the KS equation. So by here, we specified that KS equation, KS is equal to A, and then we have E raised to EA is divided by RT. Okay, that is your equation.
Just a second, Evan, I'll just interrupt. Actually,
Yes,
there
ma'am.
are many requests from the participants to go slow.
Okay.
So, yeah. So
Okay,
just
ma'am.
keep it in mind, okay?
Yes, ma'am. Yes, ma'am.
Yeah, thanks.
Okay. So once, okay, I'll explain the create fields again, a little bit slow this time. So the very beginning, you would have a scalar, okay? We want to introduce two scalars. So we have scalar 1 and we have scalar 2. So this is where you will specify your initial boundary conditions for scalar 1 and scalar 2. So that is why we're introducing it under wall scalar 1, scalar field. So these will be your boundary fields or your initial boundary conditions. So this is where you will specify that within these two blocks. And then you have your velocity and you have your temperature. So these two are already there in the original solver. So you can just copy those over into your modified files. Okay. Then once you're done with setting up your initial boundary condition files, you move on to the transport properties. Now in transport properties, in the original file, you have within transport properties, you just have the diffusivity and you would have some additional parameters. I can open and show it to you. It will better help understand. So this is your modified folder. So under transport properties. Okay. So this is your original transport property. So you would have DT and you would have nu. You would only specifying these two parameters. Okay, that is your diffusivity and your kinematic viscosity. But in your modified folder, so you see in the modified folder, we have additional parameters. Now, if you were to just type in these parameters within your constant folder, OpenFOAM would just neglect it because these are not defined in your solver itself. So it will just try to bypass everything. So it would only see DT and it would see nu. But over here, we want to introduce the diffusivity for scalar 1, scalar 2. We want to introduce rho, CP, kappa, and then we want to solve the RNA's coefficients as well. So all of these have to be introduced. So to introduce these, you would modify your header files as well as the .c files for those to be solved during your equation or during your simulation. So over here in your transport properties, we are mentioning that we want to solve first for DS1, that is the diffusivity of scalar 1, then for diffusivity of scalar 2, and then we want to solve for RNS equation. So in RNS equation, we specified the coefficients over here. What are the parameters that need to be solved and which are the constant parameters you need to type in your transport properties? Those are mentioned over here. Similarly, you have introduced that KS block. So if you see this, so over here, you have the KS block. Within these, you have type RNS, and then you have the parameters of this. So these are specified in your header file. Okay, the original header file. This is your modified header file. Now, once you've done modifying your header files, you can go to the .c file. So within .c, as I was explaining, anything you want to solve during your simulation and all comes within this while loop. And if you mess up something over here, you will obviously get a prompt on the terminal itself saying that a particular line in this particular code is not proper. So you can rectify those. I'll show you how to get started with the modifying part of a solver as well. OpenFOAM has its own documentation, so it will be very beneficial for you. So the very first thing you want to solve is this KS equation. So we've mentioned all of these parameters in the header file. So it can fetch those headers, and so it'll know like what is A, what is EA, what is RT. So all those parameters are mentioned over there. Whereas in the original file, it is only solving the T equation. Okay. So this is the difference. In the original scalar transport, it is only solving for temperature, whereas over here we are solving for scalar 1 equation and scalar 2 equation. Now again, in scalar 1 and scalar 2, now I'll show you the equation back again. So this was our original equation. Okay. So if we just rearrange a few of these, like if you take the diffusion term and you bring it to the left-hand side, you would have a minus sign in front of it. And where you have minus RC, that is your reaction term, you can replace that with Kc. Okay. So you can remember this equation, you have d by dt of C plus the velocity term, that is you can take as phi, and then you have your gradient and you have C. Okay. So the same thing is over here. So you have FVM. So we're using finite volume method. And over here, you would have d by dt of scalar 1. Okay, so this is your first term. Then you have phi and you have C. Okay, so over here, again, you have scalar 1. So you have plus FVM of divergence of phi, and then you have scalar 1. Okay, and then you have minus. As I said, if you rearrange this, you would have this diffusion term coming this side, so you would have a minus sign. So minus and this term, so you would have minus Laplacian ds1, that is your diffusion term, and then you would have scalar. And in the end, equal to Ks of scalar, so basically multiplied by scalar. So this is your temperature dependent part. You're on the right hand side. Okay, now this will be solved using Readiness equation. That's why we mentioned on top over here that Ks over here, this Ks will be found through this equation. So we've done this for one scalar 1 equation. Similarly, for scalar 2, you can just repeat the whole thing. You can change the name to scalar 2. Now, in case we were to have additional scalar, so you can again increase these blocks into multiple blocks. And then you have some relaxation parameters and all you can set. So those are set over here. So with this, you have specified and you have introduced the equation in your C file, that is in your modified solver. And you have also modified the header files. Anything that is dependent on those equations, you've mentioned those also over here. Okay. Now, once you've modified all of these, how do you compile it? So this is where you would go back to your case file that we have. So you would have the case file, you would go to solver and you would open it. So, okay. So once you're within this, basically you have the header file and you have the C file, you can right click, you can open in terminal. Is the text visible? Can somebody just say yes or no?
Yes, it's fine.
Okay. So you can just type WSL, enter the Ubuntu environment, and I'll type OF9. Most of you must have created an alias, so I'm using OpenFOAM 9. Now, the very first thing you would do once you're within this folder is type wclean to clean anything that was previously made or any residual files that are remaining in this. You just clear the whole thing, and then you can type wmake. So when you type wmake, it will start compiling your solver. It will start reading that .c file. It will read the header files. Anything, if anything is missing, it will just show it in bright red. It can show it to you. So say we have this equation, okay? Or we have this one. And now over here, we've defined Ks and we've told to solve this equation. So suppose I would to comment out this part and I would say wclean and wmake. Okay. So let's wait for a minute. Okay, so it did not throw an error, but if I were to solve this, it wouldn't know where to fetch any of these equations. Okay, let's say over here, we delete something out. Some of the header files. We'll remove this header file. Let's save this. Let's try again. Oh, so see, if you miss out any of the header files or you don't define something, it will throw errors like this in bright red. It will show that error KS was not declared. Then mag phi, it does not understand what are these parameters. That's why if you do not mention those in your header files, your C file won't understand where to fetch those things from. So we'll save this and we create again, we compile our solver. So if you don't get any errors, that means your solver is compiled properly. To test those out, you can always go to one of these folders. Like for now, I'll show you the testing part later. So before going to the folder itself, I'll show you where can you find out a documentation to modify a solver. Okay. So if you go to Google and you just type OpenFOAM Programmer's Guide, the very first option that you have, you can click that. So over here, you can download this PDF. Within this, they have mentioned what and where you can change things. If you are developing your own solver, how can you do that? If you have any equations that you want to set. Now, I told you about the FVM and there are different methods, like finite volume method is there. So those you can find on page 35. Okay. So over here, if you're solving for a Laplacian term, and these are some of your this, so you can type Laplacian phi. So anything that you are like, we would write it in simple Greek letters. You can mention those in a coding language pattern. So how OpenFOAM is designed, it gives a whole document on that. And additionally, most of you might know this or might not know. If you scroll down a bit, scroll on top, there's one particular table that gives you the dimensioning of what and where exactly are the dimensions set to. Because most of us, when we copy out a tutorial, we don't really see the units that we are putting in. Okay. So over here, if you have that, like if you open any of the files and you see on top, you have a set of numbers over here. So if you have a velocity, you would have meter per square, something like that. So all those parameters here, it mentions that first one in this whole section is mass, second one is length, time, temperature, quantity, all those things. So you can go through this document. It's a very detailed document. It is really good if you're trying to develop something on your own. So it specifies everything, how to incorporate an equation within OpenFOAM environment, what particular header files you would require, how to find those, all those things are mentioned within this document. So you can have a read of this. Okay. But coming back to the case that we have, so this was a case. We have compiled our solver under solver setup. And now you would have two additional folders. Okay. One is for plug flow, other one is for laminar flow. So I'll show you the domain that we have. So this is our domain. It's just a 3D pipe. We have an inlet, we have an outlet, and these are the walls. Now in this, we are going to be introducing the scalar at the inlet. Okay. We are keeping scalar 1 as 1. That is, means we're giving scalar 1 and scalar 2, we are keeping it as a product. We want to see how the scalar 2 develop. So we are giving the whole inlet as scalar 1. But before we do that, we have to first initialize the flow. So we will first solve simple form, but just to get the flow parameter out. Then we would solve the energy equation using scalar transport form, that we will get the temperature equations and all of those. And then we will copy those outputs into the input of your scalar transport form, the modified one. Okay, so I will explain that. So first we have the laminar flow. Okay, you can open this, you can open either of these. So you can open steady, and then you have the flow and you have the steady scalar. So if you open this particular file, you can go to the control dict. This is where you can see the solver that is being used. So then close this part. You don't really need this now. Okay. So now in this particular flow case, as I said, first we will be solving for simple form, and then you have to change.
Even please increase the font size.
Okay. Is it visible now?
Yes, fine.
Okay.
Yes.
Okay. So as I was saying, that in the flow case, you would first have to solve the simple algorithm to generate out the velocity. Then we would have to solve scalar transport flow to generate out the temperature values. And then we will take these two values, that is the output of this particular case, and feed it in as an input. Okay. I know it's a bit complex. For at least a beginner, it is too complex, but once you start learning OpenFOAM more, you will realize that most of the solvers, whenever you're solving for additional parameters like these, you have to initialize your flow first, and then you can go ahead and remove some of the additional parameters that you require to solve. So these are pretty much common once you start understanding OpenFOAM and CFD as a whole. So in our case, we will be solving first the flow equations and then the temperature equations and feeding that to solve the scalar equation. So first, can show you. So if you notice, those were the simple and the scalar transport form, and this was for the flow. And if you open the steady state scalar, and you again open control dict. So over here you have our modified solver. Okay. So this is where you will be solving all the equations that we've put in there.
Even I'll just interrupt once again.
Yes.
So please take out 1 minute or 2 minutes of time and please fill it up. So the form will be here till lunch break. So if you are doing something on your laptop, you can just take a pause of 1 minute and just fill up this form, and then you can continue with the hands-on session. Thank you.
I'll wait for say 2 to 3 minutes. You can fill out the form and then you can just give a thumbs up or something. Paris, can you just let me know once they're done?
Yeah, sure.
We are giving you 1 minute or 2 minutes of time. It's 12:31 by my watch. We can start after 1 minute, like 12:33 we can start.
Yeah, many of the participants are posting thumbs up. So
Yeah.
You can go ahead.
yeah,
We have over 200. So
let's wait for some time.
yeah, let's wait for another 1 minute.
Sure.
Hi, hello sir, can you hear me, sir?
Yes, okay.
Sir, I have a doubt while compiling the solver or while modifying the solver, should I use the pre-compiled version or I have to debug the OpenFOAM? Because I have pre-compiled also, I have debugging also. So which one should I use?
I did not get what do you mean by pre-compiled or decom, the other one.
The pre-compiled version that is available in OpenFOAM website from openfoam.com.
Okay. So
And
you
the
are asking whether
debugging
you can
version.
run it on your normal OpenFOAM or your basically compiled OpenFOAM, right?
Yes, sir.
So you don't really need to do any of those. You can run it as it is and just type like how I type wclean and then wmake. So that's why these files that we have, which are completed by our intern, we have already checked those. So you don't necessarily need to do anything more. You can always read the README file. In that, they always mention how are you supposed to run a particular folder. If there are any changes, then how to make those changes. So all those are mentioned in the README file. Okay. So you can just type wclean and wmake and you should be good to go.
Okay, sir. Thank you, sir.
Okay, so I think we can continue.
Okay.
Whoever is left, you can just fill it up after the demonstration session. That also will be okay. But please make sure that before leaving the meeting, all of you should, fill it up. Thank you. Yeah, Evan, you can continue.
Yes, ma'am. Okay. So going back to the flow case. So first we will solve for the flow and then we will move on to the scalar part. So again, within this flow file, you can have a README file. This README file will mention how to run this case. Okay, so first it says to open the directory, run cd command, block mission, all those stuff. So what we do is, so first we will just run the all run flow UP. The README file says you should first run the all run flow UP, that is your velocity and pressure. And then you have to make the change in your control dict. So from here, you have to change simple form. You can just comment it out and then you can enable scalar transport form. Okay, you can do this, or for those of you who are already comfortable with OpenFOAM, you can try modifying this case as well. So again, there is a lot of scope in modifying these cases. You can create your own custom solver which will solve for velocity and temperature together. So you can make your own solver within this as well. So again, you can take it up as a added thing. If you want to try, you can try. So for this particular demonstration, first we will run the all run flow UP. So we will open this, we'll see the commands that you have to run. Okay, you can ignore the very first command. So you have block mesh that will create your mesh. For those of you who are new, you have a set of commands in OpenFOAM that when you type it in your terminal, it will execute a specific thing. Like you have block mesh, it will create your mesh. Then you have decompose, it will decompose your domain into a smaller section, you can say. Like if you have, say my screen is this big, it will decompose it 8 times. Like it will separate or it will break this screen into 8 particular pieces, and it will solve each of those pieces on a particular processor that you have. So now if your processor has 8 cores, you can break it down into 8, and each of those cores will solve a particular section of your domain. So that is what your decompose does. NPI run is just enabling your parallelization. So if we're going to run this in parallel, now on my system, I have 6 cores. So I can drop it down to 4 because I don't want to load all 6. So I will change this to 4. And if you have 8 cores, you can run. So there's a handy way to check how many cores you have on your system. You can type ls CPU, and you can then just scroll on top. So over here under cores per socket, you will have it mentioned. So in my case, I have 6. So I will keep it at around 4. Can decompose my domain in 4. Can close this terminal. So I've changed this to 4, but only changing in your all run folder is not going to do much. So you have to go to your system, and within system, you would have a decompose pardict. For those of you who already know this, it is really irrelevant. We'll know how to change that. But for people who are new, it's a handy thing to keep in mind. Otherwise, you might face some error when you try to directly run the whole case. So you can change this number of subdomains to 4, because I think most of the people will have 4 cores at least. So once you're done with this, again, you can right click, open in terminal. You can type WSL OF9. So I can either manually type each of those commands, like I can type block mesh, or I can run the all run file. Do bash all run UP. Okay. So first it will start executing my block mesh. So you can see it's creating the mesh first. This will take a few seconds because the mesh is not really that robust. So once it has created your mesh, it will start to decompose. So I have specified mine to 4, so it will decompose it into 4 domains, 4 subdomains. And then it will start your simulation. Now the simulation is set to 50. So now it's starting at time 1. It will take some time though. Okay, so I already have this case that is already run. So once you are done, stop this. It takes some time. Okay, so you can press Ctrl+C to stop the whole equation, whole simulation. So once you're done solving for you will get some, see over here, I have this run case flow. So I've solved already. So it will give you one file that is 50. So you can copy the U folder from this into your 0 folder. Okay. So you will copy this. So you open 50, you copy the U file from here and you place it in your 0 folder. So once you've done this, go back to this case. So once you've done that, you go to system, control dict, and you change this particular application from simple form to scalar transport form. You do this, save this, can go back, and then you can do an all clean, because the all clean won't really remove the 0 folder. So bash all clean. Okay. Refresh it. So again, now once you've done that, your 50 folder is gone, but that U folder, what you have copied from that 50 will remain inside this. Okay, so see, now this is the original that I have. Okay, so this was your original U file. But once you copy the run case file, it's coming in the middle. So this is the run case that I have. So if you were to open this U file, so you would see once you run that simulation, it will store some data. So we need this data for the temperature. And then once the temperature is also solved, we need this run data for the scalar. Okay. So this is what I mean by when you're copying a U folder into your 0 folder. Okay. So once you've changed in your system, control dict, you've changed the application, scalar transport form. You can then run the all run flow T. Okay, so we'll open this folder. So you see again it is block mesh, decompose par. Let's change this to 4. And here it is solving scalar transport form. This will solve your energy equation. So once you're done solving that, you will again get that 50 folder. Like over here, you will get this 50. I've completed it for U and for T. So once you've got this 50 folder, you can copy this entire folder into your scalar steady state. Okay. Now in your scalar, I have renamed this folder to 0.org. You can also do the same. So we'll get because we require scalar 1 and scalar 2. Additionally, we require the previous run case. Okay. Like what we've run for the flow, we only require T and U from those. So you can keep those as 0.org. So you can then view those files. And additionally, you can then paste all the remaining ones. So over here, I have pasted these files in the run case for U and then for T as well. Okay, so this is for T. So it has already solved these equations. And now we're just introducing the scalar and we want to see how does that scalar move. So you can see the scalar 1. We have just mentioned it as 1, that is that inlet. So at the inlet, it is completely coming. So we have that. Whereas for scalar 2, we have set it to 0 because scalar 2 would be a product. Your first one is going to react and then we want to see what happens to the product itself. So again, if you have multiple scalars, you can check. We have a lab migration dedicated to how this particular scalar thing works. So you can check that out as well. So on our site, we have a lab migration. If you scroll down on the left to lab migration, we have this lab migration. You can go to completed labs and the very first one, stimulation lab. Within this, we have the exact same thing, but without the RNS equation. So we have solved same thing. You're checking scalar 1, and over here we've introduced say scalar 1 in the top half of the cylinder. Then we have scalar 2 generating at the bottom half. So all those combinations are there. So you can check that out also if you want to understand more about the scalar part. Now in this particular demonstration, we are just showing you how to modify the solver. We're not really diving deep into the scalar part. So once you have done that, once you've copied your 0 folder and modified everything over here, you can go to the. So this is how it will look for you. You would have this basic 0. So I changed this 0 to 0.org and made a copy of it as well and named it 0. And I pasted all my TU files inside this. Okay. So once you're done with this, you can again use the all run file. This all run. It is again block mesh decompose. Then you divide your whole domain into 8 parts. Here in my case, we'll divide into 4. And here is where you will run your new scalar form modified in parallel. And then you reconstruct the data. So let's go back to the run case. So this is the run one. So you can open it. WSL, OF9. And you can open this in Paraform built-in. The reason why using built-in is because in the regular Paraform version, for some reason, it does not show your So this is your pipe. You have the pipe geometry. And so over here, you can see the temperature, velocity, Ks that is solved, scalar 1 and scalar 2. So all these parameters you can view. Now you can read the report. In that they have changed a few things. They have mentioned what they're trying to find, what results. Now this one, I only showed you about the modification, but in that one, they were trying to find out the residence time in the pipe itself. So all those parameters they're trying to find out. Let's take a slice of this. Slice. Let's say scalar 1. So on the left-hand side, we are giving a scalar. And then as time passes, you have the scalar moving from left to right without disturbing the flow. That is why we've initialized the flow first, and then we are introducing that scalar within that initialized flow itself. So this is the whole setup for this case. Now in the lab migration that we have, in that we had introduced two scalars. Okay. So one is on the top half and the bottom half is a product. So when this top one is forming, and we've introduced diffusion in that as well. So if you increase the diffusivity term, so in this, you go down to constant and you open transport properties. Okay. So over here, we've set diffusion to 0 for scalar 1 and scalar 2. So you can play around with all of these factors. Now, most of the parameters are set for water. So all these remaining constant parameter will be for water, whereas your diffusivity, you can change based on how you want to simulate or what you want to find. So if you want to just check what happens when you increase scalar 1 diffusivity or scalar 2 diffusivity, you can increase that. You can put it as some factor over here, can increase the diffusivity of your thermal diffusivity as well. You can change all of these parameters. You can see how it affects your whole simulation. So all of these are possible just because you have modified your solver. If you were to just simply add these names and these dimensions into your folder, you won't really get anything. And it might even give you an error if you put that solver name because it has not compiled anything. So in order to compile a solver, you need to first modify the header files. You need to introduce the equation you're trying to find, and then you can compile that and you can run it in your simulation. Now, in our case, the simulation itself was quite complex, but in your case, you might just want to incorporate temperature in a simple algorithm. You can do that as well. There are many people who have done that. You have solvers for that as well, but if you want to try something out, you can do that. You can always introduce temperature within the simple algorithm. Or if you have some multi-phase case and you want to introduce another thermophysical property or another property that you have, you can always modify that as well, add in those equations, and you can do those things. So there is no limit when it comes to modifying anything in OpenFOAM. It's as Mr. Advait said, it's an open source software. You can play around with it. If you have something specific to your case, you can always model that entire solver from scratch, or you can take help of pre-existing solvers and you can just modify those up to a level that is satisfiable to you. So there is no restrictions when it comes to OpenFOAM. That is why we try to tell people to learn OpenFOAM, because these restrictions are not there. Like if you were to do the same thing in ANSYS or in any of the other commercial solvers, you would have to write your own code or try to post-process something in that end. But here you can do that in the front end, in your back end itself, and you can do it in your simulation stage itself. You don't have to really post-process the additional data, or you have to put some additional parameter and then try to find out something. Okay. So this was it about the whole solver modification part. Now, if you have any questions, I'll be happy to answer that. If it is too complex, we can always take it up at the 5 o'clock Q&A session that we have. Yeah. So thank you. So if you have any questions, you can ask now. There are a few questions.
Hello.
Yes, Mr. Ranjit.
Actually, the instruction went very fast as I saw, but just following the video that is available, I guess we could do it, right?
Yes, you can always refer to the video. Now all these sessions are recorded, so you will get a recording as well. You can slow it down if it's too far, because we only had 1 hour. So in 1 hour to explain everything, it becomes a bit difficult for us as well.
Yes, I understood it. only thing is that just by means following the steps, starting from downloading and then copying it in the directory, everything can be done, right?
Yes. It is a simple copy paste, and you have to only read the README file. You will be able to do the exact same thing that I've done right now.
Okay. Okay. Thank you.
Can't we use the same mesh while solving for T after U? T after U, you are using the same mesh. Okay. So in the flow simulation, you're only changing the solver, whereas your mesh remains constant. Okay. I think that is the question by Mr. Abhishek. Okay. Most of the questions Pariv have answered.
Excuse me, sir.
Yes, Himant.
How can we change the element size, sir?
Sorry.
How can we change the element size
The
if
element
we
size.
require? If we require.
Element size as in the mesh element size.
Sir.
Okay. Okay. So show that. Usually this we always take it up in the basic workshops that we have. This time we are just focusing on demonstrating most of the things. I'll just show you. It's not a big deal. So
Okay.
you can go to system and you have your block mesh dipped. Okay. So
Okay.
these are your vertices, these are your blocks. So if you want to change any of the element size that you want, you can do it within these three numbers. Okay. So
Okay.
this is your X, Y, and Z direction. So depending on how you want to change the cell size, you can change it within this. Just remember that the pipe is at least the lengthwise, it is made in your YZ plane. Okay.
Okay, okay, sir. Thank you.
Yeah. Okay. Okay. What is plug flow case? Okay, so depending on the flow itself, there are different types. Now, in a plug flow, it's something like a normal thing. So if you see the more detailed example of what is a plug flow and all of those are in the lab migration. That is why I directed you towards that. You can read the report that has been made over here, because this explains there are in total 10 experiments. In each of those, they are trying to explain each of these parameters that you have questions on. So you can read all of these solutions. They have the simulation case files as well. So if you want to start off with Scalar and you're interested in learning about scalar transport and chemical equations as a whole, you can read this whole lab migration. It's really good. Is it possible to GNU plot in running condition? What exactly do you mean by GNU plot?
I guess they are asking about the residuals.
Yeah. The residuals are on, you can plot it. You can directly do this foam monitor and all this. Mr. Aditya, we had our installation sessions yesterday and on Friday. If you're still facing any installation errors, you can always email us on the email ID provided in the email. We will try to solve those issues over there. Message to work in the same Ubuntu directory as we can copy case in any directory. You can copy it into any directory. Like if you want, you can copy it into your downloads or your document as well. But remember that your username, like in my case, my username has a space, at least for Windows, because I have to add my name and last name. So that causes an error with Ubuntu because you cannot have any spaces in your directory. That's why it is always advisable to copy everything into your run directory, because that segregates out which versions also you're using. Like for OpenFOAM 2412, you have one particular directory. Show you. So if I were to open home, and over here I have OpenFOAM. So you see over here I have multiple versions. So if you're running something specifically on OpenFOAM 9, you will have those files saved in 9. If you have something in 24, you should be saved in 24. So you won't have to then think where exactly and which version are you using for this particular file. Which lab migration? Okay. So for lab migration, you can go to completed lab migration, go to completed labs, and the very first one, stimulation lab. This is by Professor Dheeraj Garg of Shiv Nadar University. You can click that and then you can view the solution. You can view solutions over here. The current case study is just an extension work of these particular labs. So that's why it is not that detailed when it comes to the flow part. It is just purely focused more on the simulation part for the solver itself, like the solver development part. How to create the new solid surface. What do you mean by new solid surface? Could you elaborate a bit, Narendra? For VirtualBox, yes, you can use, like if you're using VirtualBox and it is an Ubuntu environment, you can really open the file in any folder that you have. Because for Ubuntu, it's not really specific. It's only for Windows that we tell people to save everything in your run directory because you are using a subsystem, right, for Linux. That is why we tell you to save everything over there. Narendra, if you're asking for solid surface, create the new solid surface. Both, if you're trying to make any of the solid surface, you would have to create a mesh that you would do in your block mesh itself. So I'm not really understanding your question.
So, sir, if you don't mind, is there any limits to mesh?
Sorry?
And, is there any limits to mesh?
The only limit when it comes to meshing is your RAM. So if you have like
Okay.
a 16 GB RAM, a cell size of say one lakh, like 10 lakhs to 1 crore should be fine. Above
Okay,
that,
okay.
it will directly just crash.
It will be run or not?
It will run, but it will be very slow, and most probably it might crash also.
Okay, okay.
So for 16 GB, there's a limitation. If you're on 32 GB or 64, it is still bearable. But for
Okay.
16 on a laptop, you'll face some issues when it comes to meshing at that fine level.
Okay. Okay, sir. Thank you, sir.
In any case, how do we decide which solver uses a particular case? Because a lot of solvers. Okay. So when you're trying to modify a solver, there are some parameters and some equations that you will require, right? Now, in our case, we wanted to introduce a scalar, and we also wanted to solve for energy and the Navier-Stokes equation, that is your flow equations. So flow equations are pretty simple. You have the simple form algorithm and the simple form solver. Then for any of the energy equations, you will have scalar transport, or you will have like any of the basic solvers. Those are solving energy equation. That's why I showed you the path, right? You can go to the solver section and you can open all of these solvers. If you have the time, you can always open all of these solvers and check what equations are they solving. You can also find the same thing easier if you open your tutorial, because your tutorial is based on different types of simulation. So suppose if I want to try for heat transfer with buoyancy, okay? So with buoyancy, you have buoyant simple form. But say you want to introduce something additional. So you know that buoyant simple form is solving your buoyancy forces also, and it is solving your flow parameters as well, along with the energy equation and all of those stuff. And you want to modify something, so you can use this solver. Like you can go back to tutorials or to OpenFOAM, go to applications, to solver, and you can go back to heat transfer and you can open the buoyant simple form. And then you can try modifying those. Yeah, as Manzil said, the tutorials are categorized based on solvers. So you can open the tutorials and see which solver is it using. So I think it's almost 1 o'clock. We can break for lunch. We will meet you then at 2 o'clock. So if everyone's fine, there are no more questions. If there are more questions, you can always ask them in the Q&A session that we have at 5 o'clock. And after the break, we have a topic on water simulation and all of
Yes,
those.
sir.
On water
Hello?
industry. Yes, Arjit.
I just have one question. That is, say, for example, if I have one file that is there in the tutorial, is it means possible that that is also there in the application?
Yes.
Yes. Okay, that
Because
means
yeah,
we'll
because
get
you're not
solver.
see, your tutorials are segregated based on the solver itself.
Okay,
They are
okay.
both interconnected because they are going to be solving some particular equations. So for that very equation, you have a particular solver already in place. So they
Okay,
both
means
are linked.
tutorial and application both have the same kind of list.
Yes, yes.
Okay, okay. Thank you. Thank you.
Okay. So if there are no more further questions, we can break for lunch. We can meet up at 2 o'clock. Mr. Ranjit Desai will be giving a talk on the water sector. And after that, we have Nikhil, who will be demonstrating a multi-phase case. So for those of you who are interested in multi-phase and those kind of simulations, you can always join. So yeah. So let's wind up now. Let's meet at 2 o'clock sharp. Okay.
Yeah. Yeah, it's very good that we are going on time.
Yes.
And we'll be sharing. And we've also answered the questions that were there in the chat box. Okay, any more questions? We'll just wait for 1 more minute and then we'll close this meeting for lunch. Then we'll again be back at 2 o'clock. Okay, please try to join around 1:50, 1:55 so that we can start at 2 p.m. sharp. Okay, so we'll wait for 1 more minute and then we'll wind up.
Paris, can you just confirm if my screen is sharing or not?
No, it is not sharing as of now.
Okay. Thank you.
Yes.
Please make sure you have filled up the attendance sheet. That's very important. Yes, same link. So all these 4 days will have the same link for the workshop. Okay, I hope we don't have any more questions and all of you have filled up the attendance sheet. So thanks a lot. You can break for lunch now. Then please join around 1:50 or 1:55. Thanks. Bye-bye. Hey, just a second. How to fill the attendance form? We have just circulated the attendance. So Preeti, could you please paste this attendance sheet once more here?
Ma'am, I have pasted it in the chat box.
Just now Paris has pasted it. Attendance sheet.
Ma'am, I do have a small question.
Yeah, regarding?
Ma'am, since in the second half there will be demonstration of this multi-phase phenomena simulation. So I have gone through the open form programmer's guide as well. In that, lot of particular keywords are also there, which are very specific to open form. So kind request is that while explaining also those which are very important, because it's not possible to remember all of them right now. Could they? I mean, the demonstration be like that the important keywords, like say VOF is the volume of fluid and all, which is being used here, a specific stress or the explanation can be given so that we can recall what we have learned in that programmer's guide will be helpful. Not the coding part, but exact specific keywords.
Okay, so Evan, is that
Yes.
possible? If we request Nikhil, can he give?
Yeah, Nikhil, are you in the meeting?
Nikhil is not there. He'll join around 1:50. Nikhil, are you there? Just
Yes, ma'am, I'm there, ma'am. Yeah,
Okay,
it is
okay.
possible, ma'am. Shortly, I can give what is VOF and all those things I can explain in short.
Yeah, that would be great. Thank you. Thank you.
Yeah.
Thank you.
Okay.
Okay,
Thank
thanks a lot. So
Thank
we are breaking for lunch now. See you at 2 p.m. Rather 1:55. Thanks. Bye-bye.
Hello, Deepak, am I audible? I have logged into a new system, so testing it.
Yes, ma'am. You are.
Hello,
Yes, ma'am. Fine, ma'am.
Paris or somebody from the e-studio?
Yes, ma'am. I'm
Yes,
confirmed.
ma'am, you're audible.
Yes, ma'am. You are audible.
Audible, right?
Yes, ma'am.
Okay, thanks. Okay, so good evening. I'm very sorry. Good afternoon, everybody. Welcome back to the second half of the day one of the Industry Readiness Workshop on CFD, organized by FOSSEE IT Bombay. So the next session, the talk will be delivered by Mr. Ranjit Desai. So before we go ahead, I'll just introduce Mr. Desai. So Mr. Desai is from the Water Unit Infrastructure Consultancy, and he is a water resource engineer specialized in numerical modeling of open channel flows. He has an experience in simulating wide range of civil and environmental flow problems. He has also trained international teams and postgraduate students in numerical modeling and CFD. And Mr. Ranjit Desai is an esteemed member of the advisory board of the CFD team of FOSSEE IT Bombay. And so we are really very excited because I believe that this is going to be a very informative session for all the students, CFD professionals and faculty members who have joined today. So Mr. Ranjit, actually this audience is a mixed crowd. Majority of the audience is from the student. They are learning CFD and probably open form. So majority of the audience is student today, and some of them are faculty members also, and a few of them are also from the CFD professional background. So it's a mixed crowd today. I welcome you to this session, sir. So I hope we are ready to go, or should we wait for another couple of minutes because people are now joining in. It's 1:32 is the count now. I hope the count will increase and it will go till 200 at least, because in the morning there were around 240 people who
I
joined.
think we can wait for 5 more minutes and we can start.
Yes.
The
5 minutes.
presentation will be very short and it will be done within
Okay.
40 minutes maybe.
So till then, if the participants have any questions before the talk starts, you can go ahead.
Yeah.
Yeah. So it's open for the participants. If you have any questions for our team members, Evan is here, Paris is here. We can take up the questions also.
Madam, do you cover the interform solver that means two-phase flow or in this session? Because this is channel flow.
Yeah.
Is it a single flow?
No. So majorly we deal with interform itself. I will show what I'm intending to show is what kind of different variety of problems you can handle in water resources. And majority of the time we are using interform for that kind of a thing. So VOF based solvers. We will be showing demos on to that, the variety of problems you can deal with it. I won't be able to get into the setup and all that kind of a thing right now. It's a short session. So that we can maybe plan later. But right now I will be focusing on the application side of it.
Okay, thank you, sir.
Yeah.
Even Vimal Raj has asked a question.
In the session for fluent flow study.
Fluent flow study.
Vimal, do you mean fluid flow study or like fluent as in ANSYS fluent?
Yeah, so Vimal Raj, if you can elaborate your query, it will be helpful for us to answer. If you're talking about ANSYS Fluent, we are not dealing with ANSYS Fluent. We only train on open source software, and for CFD, currently we are training on OpenFOAM. If it's a fluid flow study, it is very general question. So we are confused with the question.
I think Vimal has said ANSYS.
Good afternoon, sir. It's Vimal, which I asked for the fluent flow study. Since I'm working in the aerodynamic study in the Journal of Fluent Flow Study and Structural Flows and CFD, CFX. I'm currently working on the aircraft models, currently working on it. So I need to know, is there any special open form operations for fluent flow studies, which is currently related to the ANSYS? That's why I'm asking about it.
Yeah, I mean, before switching to OpenFOAM, I used to use ANSYS in my previous organization. So pretty much whatever you can do with OpenFOAM can be done with ANSYS as well. They have the VOF models and everything with them. But right now, since FOSSEE deals with OpenFOAM tools and we also do OpenFOAM simulations, so we will be focusing on the application of OpenFOAM for the water environment applications here.
Is there any idea to we get about the CFX solutions of for the aerodynamics? Is it possible on FOSS?
I believe like when I was doing it, the best place to start would be the software manual. And for particularly for open channel flows, Fluent is better suited than CFX.
Okay.
So you can start with its manual, and they have a theory manual and a practical manual, I believe. So it is well covered in that manual.
Sure, sir. I'll go through it.
Yeah.
Thank you. Thank you.
Okay. Thank you so much.
Ma'am,
Yeah.
ma'am, in the schedule there was mentioned about the introduction to OpenFOAM and CFD. No, ma'am. Are we gonna have that or
It was done in the morning.
it was like
Yeah,
we
Professor
directly came for the manufacturing of that? The sir explained, no, ma'am. So before that,
No, before that, actually, Professor Chandan joined late. So we first had the session by Mr. Advait, and then Professor Chandan
yes, ma'am.
talked about safety.
Oh,
Introduction. Yeah.
oh, thank you.
If you have missed it, don't worry. We have recorded it. We will post the recording soon to all the registered participants.
All right, ma'am. Thank you.
Okay. So yeah. So with that, we can begin the session by Mr. Ranjit.
Yeah.
So over to you, sir. You can just go ahead.
Yeah, so I will share my screen. I have a small presentation, a few animations and cases, demos to show. I will share my screen. I hope it's visible. I will just go in the presentation mode.
Yes, sir.
Yeah, is it visible properly?
Yes, sir.
Yeah, okay, great. So my topic of discussion would be applications of CFD in water resources. My name is Ranjit Desai. Payal ma'am has introduced me. I head the CFD department at Water Unit Infrastructure Consultancy LLP. We have offices in Pune and Sangli in Maharashtra. We majorly do CFD using OpenFOAM just to keep our overheads low. And I started using OpenFOAM back in 2022. And I started doing CFD quite earlier than that, since my undergrad. So that would be year 2012 or 13, like that. I've been doing it for more than 10 years now. OpenFOAM, I'm quite new to it, but still quite, I mean, we handled a wide variety of problems using the solvers that we are going to discuss. So I have a MTech in water resources. I did it in 2015. BTech in civil and water management. My specialization, as ma'am told, is free surface flows, open channel flows, and the numerical modeling of those flows. So I had spent some time in Darul Handasa from 2015 to 2020. I left my job and I joined with my partner, and we started this company called Water and Infrastructure Consultancy LLP, and I had CFD department there. Majority of the work that I do is related to CFD and flood modeling and numerical modeling of such things. So the specialized tool that I use would be OpenFOAM and HECRAS. And in academics, I have dealt with multiple problems. Again, similar problems of open channel flows, vortex shedding, flow over a weir, labyrinth side weir, etc., etc. So I had a publication back then, 2015, which was on labyrinth side weirs. Am I audible? I mean, or the voice is very low. I can speak a little louder, maybe.
You are.
Yeah.
You can continue.
So these would be the applications which we normally look at in water resources. So I've categorized them into different categories and what exact applications are there. We haven't dealt with all of them yet, but I have a few demo problems and a few problems which we actually dealt with, which I can show you from this. So with dams, we have usually CFD in water resources is done for dams to assess the capacity of the spillway, to assess the pressures on the spillway profiles, etc., and the discharge capacity of the spillway. Then there comes a structure downstream of a spillway, which is an energy dissipator, which is supposed to lessen the impact of fast moving flow onto the downstream bed. So the energy dissipators are used. And these are a bit unpredictable or difficult to calculate manually. So CFD is used for their assessment of their performance. Then we have a special structure called a bottom outlet. So these are particularly used to desilt a dam. So these are again, these operate under very high velocity and high pressures. So these can also be done using CFD. Then there is a very peculiar structure called a fish passage. A fish passage is, it's not used a lot in India, but in Western worlds, it's a concern that there are migratory fishes which have to travel upstream of the river, and a dam might obstruct it. So for letting that fish pass through that dam, there is a structure called a fish passage constructed. The idea of that fish passage is to maintain a continuous stream of water, flowing water with a low velocity, so that fish can flow upstream from that. So that we also had done a demo on that, so I can show that also. And then there comes a simulation of a dam break. So this is particularly, it can be done with OpenFOAM, but we usually do HECRAS for dam breaks. So a dam break is basically if a dam bursts, what happens downstream of it. So a lot of water is released in a very short amount of time and it floods a lot of area. So how much of an impact is going to happen? That assessment is done using dam break studies. So in treatment, we do flow distribution, some energy distribution structures like drop shafts. We do mixing performance analysis, residence time distributions. Then if there are any pumps fitted, so we do the pump sump analysis for that kind of a thing. There are some processes which require aeration and how the air is getting dissolved or dispersed in the fluid. That kind of studies can be carried out for treatment plants. Siltation and aeration are kind of an, it's a multi-phase application. So these kinds of studies can also be done. Then we deal majorly in water resources with conveyance networks. So it can be water supply networks, it can be sewerage, it can be stormwater. So these three major networks we deal with, which carry water from one place to another. So these networks have transitions, like one large pipe coming in and then it might transition into a rectangular channel. A pressurized system can be converted into a open channel. These transitions are a little bit difficult and tricky to predict. So there we use CFD. Drops are another thing. So sometimes we have to, depending on the elevation profile or depending on the slope that we are following, we have to drop the channel or the pipe by a certain height. So these drops also have to be designed and analyzed using CFD. Junctions are another thing. I have one simulation for junction here. Outfalls are very critical for disposing of any water that is coming out through the systems, particularly for treatment plants, wastewater treatment plants and such things. We have control structures which are weirs, gates and such things, and there comes an uncertainty of predicting how much flow is going to pass through that structure, and CFD can help in that. Siphons are also a very typical structure which can be predicted, but CFD helps in assessing the head losses and such things in a siphon. Hydropower is one application where we have a lot of adoption of CFD early on, and particularly for the intake structures, the tail race channels, if they have any manifolds or such things in a penstock or something like that, CFD can be used. We are exploring the silt traps. So a silt trap is basically a structure or a device put in place which can remove the heavier particles in water, the silt, before it enters into a turbine, because silt can erode and cause damage to the turbines. Silt traps are usually designed. This is also a multi-phase application for CFD. Then in environmental flows, we have two types of, one is air quality or air dispersion kind of study. This usually industries have long chimneys, and if they have any emission, they have to assess how it is dispersing and whether that pollution is coming down in certain limits after a distance. So those kinds of studies can be done with CFD. There are other methods of doing it also. Then there is a pollutant transport phenomena, like it's a transport phenomena, diffusion phenomena that happens. This is generally done for if there is a sewage line which is disposing of in a in a water body or in any place. So these kinds of studies are required so that the pollutant will be dispersed and the concentration lowers to a certain limit which is acceptable. These kinds of studies can be taken on. So I'm going to present you two things, a few demo studies, the demos we did for showcasing our capabilities and our possibilities of doing certain kind of studies to our clients. So, and the other one is the kind of projects we actually tackled in industry in last 2-3 years. So we'll start with demo studies. This was the first problem I dealt with in my professional life, starting with CFD. It was a simple problem statement. So we usually have these kinds of channels, trapezoidal channels, beside roads. So these are supposed to carry excess rainfall coming from roads into a nearby culvert or a nearby low-lying stream. And what happened was they had a light pole foundation coming into this channel, and they wanted to assess how it affects the discharging capacity or how it affects the flow in that channel. So this problem came to me, and this was an interesting problem because this showcases that a low velocity flow can transition into a high velocity flow if you put an obstruction into it. So these are the kind of problems you deal with within open channel domain. So you have a low velocity flow, which is we call subcritical flow, which is transitioning into a supercritical flow. Now, if the channel is earthen channel, that high velocity can erode it and carry, it can erode it, make it deeper, carry the material with it downstream. So this was not something which was desirable. You can also see very beautifully in the simulation that there are some cross waves which are happening. These kinds of fluid structures are really difficult to predict analytically. So this is the beauty of numerical simulations here. Then this is a demo for a study which we can take up. Like if you have to bring water from a high to a lower area, this is a very general problem we have. So how to dissipate the energy of the water which is coming down, because with height, water is going to accelerate. And with CFD, we can study multiple kind of options really fast. So this kind of a study barely took me a few hours of doing, and we can really see which structure would benefit, which structure would dissipate energy much faster and all that. So if you can see if there are only steps, so the flow will accelerate, will have a higher velocity going down. If you have chute blocks, you have a lower velocity, and if you have steps with keys, it is even better. So that these kinds of studies, we call it optimization, I mean design optimizations. So these can be taken up with CFD very easily. The only alternative to this is going for physical modeling, which is again very expensive if you want to make any modifications and test, and they take a lot of time. CFD is much faster than that. In hydraulic jump is another energy dissipating structure, like the one I was speaking about earlier regarding energy dissipators below a dam. So hydraulic jump is a type of phenomena that is used to dissipate energy. This was I took up this project during my MTech seminar, and we tried to simulate and had this thing going on. So I used ANSYS that time, but I tried to replicate the same problem in OpenFOAM, and this is a 2D problem, 2D OpenFOAM. By the way, for most of these, I'm using interfoam or inter-isofoam solver. So this is a VOF-based solver. It has a two-phase formulation to simulate air and water flows. So we can see that a high velocity supercritical flow is coming in, and it is merging with a low velocity subcritical flow. So this is called an hydraulic jump. A lot of air bubble entrapment happens at this jump. And this is a bit tricky to set up and do, because OpenFOAM does not come with a pre-built downstream water level condition. So I tried to do, this is a custom coded boundary here. So I tried to do that. I believe I have used coded mixed value boundary condition here. Yeah. So the fish passage I was speaking about, it's something like this. It's a structure something like this. So this is an upstream portion and this is a downstream portion, and the water flows continuously from this structure, and we can assess which are the high velocity and low velocity areas, and if the fish is having a continuous passage of that zone of low velocity area, so that it can pass upstream. So there are multiple ways to visualize it. I have just color coded it just made a contour of high velocity areas, and they show the pockets of high velocity, and whatever is in between is a low velocity area. So fish can pass through that. A spillway example is here. I mean, this is a special type of spillway. It's called a morning glory spillway. So a morning glory spillway is usually situated upstream of a dam. It has a downpipe which is bent and it carries the water downstream of a dam. But the start point of it, which governs the flow into that whole spillway or that penstock, is this structure particularly. So it has certain design guidelines. So what I did is design the structure using those guidelines, and I wanted to see what happens if I subject that structure to a discharge which is higher than design discharge. So I believe I have given a 2 or 3 times higher discharge here, subjected to this, and then I tested what happens here. There are really interesting things happening here, like it maintains a air core particularly. So if you can see it here, these two shafts going down, so these carry air down into the shaft. They should be maintained. Then the other thing here you are looking at is a pressure profile. So this is a plan, you are looking at in plan, and this is in a elevation. So you can see that there will be negative pressures coming in when the highest design discharge is hit. So here there is a transition from this profile to a vertical pipe, and wherever the joint is, you have the highest negative pressure. So the negative pressure causes cavitation and erosion of that structure. So it's not desirable there. So this is what happens when you subject a structure to a higher discharge than what it is designed for. This was an interesting problem that I did. Usually spillway problems are interesting because one is a discharging capacity, and then you also have to look at the pressure profiles and quantify them. This can be seen really well. Another thing in this particular one is time varying boundary condition. So the discharge that is incoming is time varying. So that was implemented here. Then this is a very common structure when there is a combined sewer. So a combined sewer basically is there are generally, ideally, there is an idea that storm water is carried in a different sewer and a sewage or wastewater is carried in a different sewer. But storm waters are designed for 5 or 10-year return periods. So for storms which can carry less water. So just to increase the carrying capacity of a storm sewer, sometimes it is connected with wastewater sewer. And that connection happens through a overflow chamber of some kind. So this line coming in is a storm sewer, and this line going out is going out to the wastewater sewer. But what happens is we have to divert the flow from one sewer to another, and usually it happens through side weirs or some kind of that structure. So it's really difficult to predict how that flow bifurcation is happening or how much quantity of water is going in which branch of that sewer. This can be really beautifully predicted with CFD. So this is what we are seeing it, like some water is getting diverted into the wastewater sewer and some water is carrying forward into storm sewer. So this can be quantified, like discharges can be precisely measured using CFD. And we use this kind of thing for particularly flow bifurcation wherever it is happening. Then one more interesting structure is a drop shaft. So this particular one is a tangential vortex drop shaft. So the idea behind a vortex drop shaft is we try to inject water in a vertical pipe in a manner that it clings to that pipe tangentially and it rotates along that pipe and goes down. So the idea here is that because of the skin friction between that pipe and the water, the velocity will not accelerate or the energy dissipation will happen to a certain extent. I'll show that here. So CFD becomes really critical here because it's again very complex 3D flow which cannot be analytically predicted. There are so many things that are happening, like the flow is coming in here, transitioning into a subcritical flow, then it is getting into a tangential manner, rotating into that pipe. It is also sucking in air, and that air core has to be maintained. This cannot choke here. Then when it comes down, how much it is accelerating, at what velocity it is going to impact in the stilling basin down, whether all that energy is getting dissipated or not. All these things can be analyzed using CFD very beautifully. So this can be done very easily, tangential drop shafts. So now we will look at, these were the demo cases mostly, which which we just did to showcase our capabilities. Now we are going to look into what kind of projects we do or what kind of projects we have done until now. So this is again a study of flow bifurcation, but this was done for a treatment plant. So the flow distribution for SBR tanks. So SBR is a sequential batch reactor type tank, like treatment plant. So sequential batch reactors are really large tanks where wastewater is dumped and then it is treated there. It is allowed to settle and some reactions, aerations, and all those things happen in those tanks. And before the water, usually in a treatment plant, what happens, the water is coming in through a single channel. And then that channel has to be split into multiple channels and the water has to be delivered to multiple tanks. So a distribution box come in between that, and it helps to divide that single stream of water into multiple channels. So the original design they had was of this kind. So one inlet channel coming in, turning 90 degrees, then the water is underflowing from this underflow inlet, then overflowing from these weirs into individual channels. So there were 3 weirs for this tank and one inlet on one side. What was happening was the flow was not getting distributed as desired. So we ideally require that flow to be equally divided between these channels, which was not happening. Then we suggested an alternate arrangement. So we deepened the tank, shortened the weirs, and put baffles here to correct the flow. And we can look at the results there. So these are basically the boundary conditions here. So we have an inlet here, a top or atmospheric boundary here. Everything else is wall, and then outlets here. So I placed outlets here like that because I wanted to control the downstream heights of those things, or we can keep it free flowing as well. So this will not hinder into, it will not cause any backflows or something like that. So you can see these are the plan views of the same geometry. You can see that the flow is coming in, turning in like that, and then circulating into the tank. And most of the flow was passing through channel 1. So the channel 1 is carrying just a moment. So the channel 1 is carrying 2.1 meter cube per second of flow, 2.21 meter cube per second of flow, which was excess to what is required, so which is 2 meter cube per second. Channel 2 was carrying what was desired, and channel 3 was carrying much lesser flow, so 1.56 meter cube per second, a lot less. So percentage wise, you can look at it here. I mean, we required it to vary between plus minus 5% of what is desired. And the original had overshoot of 2.21% and 1.56, 2.21 meter cube per second and 1.56 meter cube per second. So that was a quite huge deviation from what was required. We did the modifications, we added the baffles and everything. And on the dark bars, you can see that it is within that desired limit which we wanted to have. So these kinds of studies we did a lot in last 2-3 years for very large treatment plants in Mumbai. This is another structure where we are again studying flow distribution in multiple channels. So this is, I will just take a moment to describe what this structure is. So these are vortex grid separators, these round structures, and these are the screen channels of a treatment plant. So what happens is the water comes in through these pipes from bottom into this tank. It goes into the screen channel. Whatever trash is there is supposed to be caught by this screen. The water passes down into this grit chamber. So even if you filter the trash, the water might be carrying some fine particles which are of sand or some grit or some solid particles. So these chambers are designed to separate them. And then the water collects into again one channel and goes forward for a pumping station. So the idea was here, I mean, again, same. They require that the water to be divided equally into each channel because they wanted to utilize every channel equally. If that doesn't happen, some screens might fill up faster, some chambers might fill up faster, and they can cause higher maintenance in those chambers. So they required the flow distribution to happen equally here. Another interesting thing was here we implemented a porous zone to incorporate head losses happening at that filter screen there. So we can see it here that the water is coming in from the bottom and causing these 2 humps here. And then it is getting divided into these channels and then getting into these 4 vortex grid chambers. This was particularly tricky because all of this is subcritical, and this water level was very critical for them. So we had to find a boundary condition to maintain that water level there. That's the trickier part. And the other trickier part was this porous screen. So figuring out the porosity coefficients is something that you can do on, I mean, with certain calculators and something. We were using this Darcy Forchheimer model for porosity in this particular case. So you can specify Darcy coefficient and you can get a head loss or pressure loss happening across that boundary in some distance. This was the first commercial project for water unit which we did. It is a drop shaft. So the problem statement was the client wanted to bring water down from almost 10 meter of height. So inlet works were at 10-meter height here. And then they had a pump sump which was down here and they wanted to lower water safely. This was all coming in raw sewer. So they did not want a vortex shaft or something like that, which can get clogged. So we devised, this is a baffled drop shaft. So there are baffles here, which will lower the flow slowly. This is a geometry and this is all the boundaries that we assigned there. And this was very intricately designed, like many considerations were taken into this because since this was a raw sewer, we sloped these baffles, filleted them and all those kinds of things were done and then they were incorporated in the model as well. So this is the simulation animation of that kind of thing. This is done in Paraview. All this camera motion and everything, it is done in Paraview. So the idea here for a drop shaft is that this jet has to fall on the baffle, not on the wall. Then the energy dissipation will happen and the water will not accelerate beyond the limit going down. So the baffles are designed like that, and the space between baffles should be sufficient enough so that it will carry the water, whatever discharge is coming in, to the next baffle. Otherwise, the whole structure will choke and sufficient water will not pass downstream. So this was done. We monitored the volume here, the total volume, and you can see that around 10-15 seconds it reaches a steady state and just goes like that. We can see the velocities here and the water volume here. It's an interesting thing. Particularly, I was very happy with the way the animation came out. We still use this animation to showcase our capabilities to our client. Client was very happy also because this was very presentable for them to their client. So this was the first project, and because of the way this turned out is they gave us much more projects after that because of the quality that we delivered to them. Then this was another drop shaft. Particularly, they had a problem here that SBR tanks, they had a 3-floor of SBR tanks. So this is very high, like I believe it is 30-meter high. And they had to lower water from each floor to the ground floor, and the drop shaft had to have multiple inlets. So we proposed multiple solutions to them, but this stuck to them and we went ahead with it. So this is a baffle drop shaft. We tried to fit it in as little, whatever footprint they were having, and we designed it properly. We tested it using CFD. So in this particular drop shaft, there was this was going to be suspended above ground, beside a building, like on the side of a building. So this had to have air vents to so that the water will not cling to the baffle. So these circular things, these are air vents. So the client also asked us to assess the air velocities in those pipes, so which we were able to give them, and we then, based on the CFD simulations, we changed the designs of these air vents as well. This is a heavily modified drop shaft design. So this is what we were doing there. So this has multiple inlets, an arrangement where the flow will not go back into those inlets, and whatever incoming flow will go only down. And then there was this scaling basin kind of a thing which dissipated the falling jet. This was a study we did or we assessed the air velocities in the air vents. And as you can see, the way water goes down, there will be air velocities there. So we quantified those air velocities in those pipes and we presented this to our client, and the client was not happy with seeing these kinds of spikes in the velocity. So we changed the whole design of this pipe. So instead of a single pipe connecting all the vents, we designed individual vents for each of the baffle. And that was how that was okay with the client, and then went ahead with it. So why I'm telling these is, these are very particular things which will come when you are working on a project. And these, you might not encounter the same thing in your projects, but Working in academia, particularly, you might not come across such problems. No one is thinking about these things unless you are having a very particular problem happening and you are trying and testing and simulating. So these things come up. And a lot of things can be dealt with CFD. This was again one more problem. This is a conveyance system for the same treatment plant. So there is a collection box here. They called it a gravity box. And then there was this 800-meter long conduit, which was connected to this outfall. So this outfall was discharging into sea. And they had a requirement that the seawater should not come into this. And this was, we had to design it as a siphon. So a free surface here, a free surface here, and the whole conduit was pressurized. And there were chambers in between, which were again having a free surface. So we placed probes into all these structures to monitor water heights, and we studied how much head loss is happening and what velocities are there. So because of these bends and everything, there will be head loss. So how much discharge carrying capacity this whole system has, we assessed it using OpenFOAM. And this was the kind of thing. So if we have a water level of 29, what is this, 29 meters at the outlet. So we were having to pass that 29 meters at the outlet. We had a 30.5-meter level at the inlet of that conduit because of head losses and everything. We could assess this using CFD. We also assessed it using manual calculations. So CFD was showing a little higher losses than what manual was predicting. So we went with what CFD was predicting, and the client designed their whole treatment plant levels accordingly from this one. Then for a treatment plant, we have another structure or another physics happening is a contact tank. So a contact tank is basically a chlorination or a fluorination tank, which comes into picture for disinfection. So the idea is that the water should remain inside the tank for a certain duration where the chlorine is coming into contact with most of the water so that it can disinfect. So the chlorine mixed water can be either the chlorine is mixed at the inlet and then left to settle. And we can see what is happening with that kind of a thing. So the chlorine concentration is coming in. And if the tank is filled, how much time it takes for the chlorine from the inlet to reach the outlet, we are calculating that, and we are monitoring the concentration of the chlorine at the outlet. So that is called the residence time distribution. That's how we get a residence time distribution. So this is a continuous flow of chlorine. It can be done as a instantaneous plug flow volume initialization as well. So that will give a different curve. This is a continuous flow of chlorine, and it will take for reaching outlet, it will take certain time, and this is called the residence time distribution curve. So based on this curve, certain quantities are calculated, like how much time it is taking for the chlorine to reach the outlet. The mixing performance can be assessed using different indices. These can be really well calculated using CFD and easily. So this was a already well designed time. We just analyzed it and submitted to client, and they were happy seeing it. Then these are the problems which are coming up recently to us. This was a demo that we did for one client. I cannot show that the original project files because these were a bit confidential for our client. It was a demo we did. So the structure you are looking at is a tail race channel of an intake. So this is a channel, flow is coming from this side and getting into this side. So these were the 10 intakes for pump, really large pumps. So this is a PSP. A PSP is basically pump storage hydro power plant. So the idea here is storing energy, excess energy into water, so that whenever they have excess energy in the energy grid, they use these pumps to pump water from one reservoir into another reservoir, which is upstream. And when they have an excess requirement in the energy grid, they release that water and generate electricity to supply that. So these pump PSPs are particularly used for load balancing. They also act as a kind of battery, a water battery kind of. So these intakes were supposed to draw water from this lower reservoir into upper reservoir. The problem here is the intakes require certain depth to operate at, and the reservoir was at a little bit higher level. So there was this dip happening into this, and the apron was sloping downwards. So where the slope started, the flow started to converge together, and this was a very interesting phenomenon happening. So the client wanted to assess how much impact it is going to have on the turbines we helped them identify what was going to happen to them in terms of head losses, in terms of if there would be any vortices, if there would be any pressure losses, what all those kinds of things we assist in this project. And we did a comprehensive study of these things. So these are for us, these are kind of new study. This is not a multi-phase problem. It's a single phase problem with the top boundary maintained at symmetry. The water surface level can be managed that way. And in this particular case, the water surface was not varying, so we could make that assumption. So some problems can be done that way. So I don't have the results to show for this thing. This was a very particular case which I did with my previous employer. So this is a dam in Africa. It's called a Kambambe Dam. There is a dam, and then there is a spillway for this dam. So these were the spillways, and then there is a ski jump bucket. So the ski jump bucket is supposed to throw water up in the air and away from the this wall. So what had happened there, the problem that came to us was they violated the gate operation. So you are supposed to open gate to a certain height to pass a certain amount of water. And because of that, they did not open the gate sufficiently enough. And because of that, what happened? This jet did not go through on the bed of the river, but it fell on these berms. So these berms are like, these are just cutting and then they're covered with some concrete. And what happened since that jet landed on those berms, they got eroded. And then there came a problem where they were discussing because of whom this happened. And then that problem came to us. You assess it using CFD and tell us what happens if you open that much gate and what's the problem. So we did, we constructed the whole, we made the whole model of the spillway and did a few studies and told them how far that jet goes onto the berms or onto the river. So we did 2D studies, 3D studies. This went on for 3 months almost. So this was a large model we did, and we settled the problem. I mean, this was wrongfully operated gates in that case. For the same dam, there was another problem. So this is the bottom outlet. So this portion here, it is connected to dams. There is a gate here. And then there were special structures called these aerators. So aerators reduce the chance of cavitation in this tunnel. So this tunnel, this was an underground tunnel, this is a very large tunnel. I mean, almost 10 meters in height, and the amount of water head over it was something like 30 meters or something like that. So a large water head. The velocities in the tunnel were in the range of 15 to 20 meter per second kind of a thing. And then there happened a mishap that this tunnel had this whole huge cavity formed due to water flow, and they wanted to assess why this has happened. These particular things, aerators, they are supposed to lower this kind of a risk, and why this might have happened, they wanted to analyze using CFD. So we made the whole model of this tunnel. This was almost, I believe, a kilometer long tunnel, and we assessed that using CFD that time. So this would be the last problem that I'm sharing with you. So we can take, I mean, the purpose of this talk was to just introduce you what kind of problems the industry is dealing with. And if you can align your academic projects to these kind of problems, it would be really beneficial for you to showcase them to employers and get hired that way. If you're going for research, then it's a whole different story. Though that requires, I mean, more rigorous and more different innovative kind of an approach and different problems. But these were the problems that the industry is dealing with right now, and to showcase that. So thanks a lot for your time. We can take questions, and if you want to ask any particular thing, I'm open for that. Thank you.
Thank you so much, Mr. Desai.
Yeah.
Participants, if you have any questions for Mr. Desai, please go ahead.
Hello.
Yeah.
Am I audible?
Yes.
Actually, for the sixth problem, that is the chlorine mixing.
Yeah.
So which solver was used?
I used Interfoam, and then there is a pluggable solver for Interfoam for this scalar transport. So it was done using Interfoam.
Okay.
But that problem, I mean, sir, it can be, see, the water level remains very flat in contact tanks. You can do using pimple foam as well. pimple foam or simple foam can also work there, but it's a transient problem. Like you are measuring time there, so I would suggest you can go with pimple foam as well.
Okay.
Yeah.
Thank you.
There is a question by Arbin Fatima. Thanks for the talk. Could you elaborate on the dam case study and what was the solver again? Yeah, so we use solver-wise, we use for any free surface flows or any open channel flows, we either go with interfoam or inter-isofoam most of the times. And the dam study, I did not show the results because again, that was with my previous employer, so that is confidential. I could only tell you a story around it, what had happened and what kind of a problem we were dealing with. So the solver was interfoam there. Laban Sain is asking, in your first case, maybe use pimple foam. So the case studies that I shared, just a moment, let me see which one was first. So yeah, so the flow distribution you are asking, Laban, you can unmute yourself and ask me. Yeah, so distribution tanks. So there is, I mean, if you ask me, I would not use pimple foam there because there will be changes in water levels, and the discharge is a function of water level over a year. So if you try to flatten that, it won't represent the actual reality. So I would still go with interfoam there. Any wears or anything we are simulating, we have to go with interfoam. Okay, so Sahil Kunyan is asking what type of mesh resolution is used near walls for these industrial cases, especially dam bottom and ski jumpers. Yeah, so that was quite a long time back. So I don't remember exactly what was the dimension of that and what was the resolution of it. But I can tell you in general what we do. So we don't try to resolve near wall flows as if we are doing an aerodynamic simulation. So in aerodynamics, it is very critical that you do that. In our case, we use the wall functions for resolving near wall flows. So that gives a fairly well prediction. We have done some validation studies also. So overly resolving mesh for particularly wear overflows or spillways, it does not result in any better solution than using any wall functions. So you can use wall functions for that. Since any closed fluid flow, should we consider incompressible, steady, or simple foam works? Yeah, so it really depends on Arbin. It really depends on the kind of problem you're looking at. So the choice of physics would really depend on the kind of problem you're looking to solve. For aerodynamics, sometimes incompressible flow works, but sometimes you have to go with compressible solvers. Depends on what kind of problem you're looking at. But if you're asking me particularly about a closed system, so if there is a pipe flow, which is a single phase pressurized pipe, you can go with even simple foam. If there is no transients happening, nothing changing with respect to time, you can go with simple foam or if there are some phenomena which is happening, like some eddies forming, some energy, some edge is getting detached or something like that. Some unsteady phenomena is not happening, you can go with simple foam. If there is some unsteadiness in the solution, you can go with pimple foam. Yeah, so Prithul is asking, hello, the question is a bit out of the topic discussed. I am actually starting to learn open foam and prior to work experience fluent, but regarding open foam, I'm a bit confused now how someone new should be approaching the learning. Would be really helpful if you could suggest a learning pathway. So, I mean, I have been, particularly for open foam, I have been self-taught. Even for CFD and other tools, I have been self-taught. For other tools, I used to read manuals and their material that they had provided. For OpenFOAM, there are certain good resources. So I have made, like you can check my LinkedIn profile. I had compiled some time ago the links to resources for learning OpenFOAM. So these would be good. And the other best possible thing for you is, stay connected with FOSSEE and get someone to mentor you there. So that would be a good start. How large would the air region be in the case of ski jump condition for the atmosphere region around the nub? Yeah, so it's very subjective. Usually, in our cases, what we do is we call it freeboard. So like particular cases which I showcased here, if you have a simple channel, you will model the geometry for channel itself. But if the channel is getting full, you leave an arbitrary area above the channel, and that should be sufficient so that it will have at least 4 or 5 cells of thickness, which will have sufficient depth for the air to move out or have some area for the free surface also to diffuse. So 4 or 5 cells is going to be enough. But for particularly ski jump, it depended like how high the ski jump is going to go, how far it is going to go. So we did some projectile calculations, manual calculations, and we sized the domain accordingly. It's a trial and error approach. You can try a few things. If the fluid is not touching the boundary, it's good enough. How the large geometry of the real industrial project can be made in open form when the dimensions of the model is also the main concern in the simulation. Atul, you can unmute yourself, you can elaborate on that question. What was that?
Hello, yes sir, am I audible, sir?
Yeah, go on.
Yes sir, like in my case, I am working on the fire scenarios in the metro station.
Okay.
So you can imagine the geometry and the dimensions of the metro station, that every features matters in the domain.
Yeah.
So that's the main concern in the open form, that how the geometry is.
Yeah, you can, if you're going, it's kind of a HVAC simulation, or you're going to go for fire as well? There.
Yes, sir, it's the fire simulation. I mean, usually we do on the FDS, that is the
Yeah,
industrial
So FBS is the best
accepted.
tool for that kind of a thing. But even if you're going for open form, you can basically use localized refinements for managing the mesh size. So that can be done. I mean, you can use Snappy for doing that, Snappy X Mesh. Or, I mean, if it is very constrained, if you're finding it difficult to use Snappy, I would also suggest that you can, if you have access to a commercial solver like Fluent or some other tool, you can bring in the TET meshes from there and use in OpenFOAM as well. So there are some ways that you can import that. So there are tools with OpenFOAM available which allows to import meshes from Fluent, meshes from other tools as well.
Sir, actually, I get the point regarding the mesh, but how my question is related to the geometry making. I mean,
How do you make the geometry?
yes, sir. Yes, sir.
Yeah, usually, see, for a metro station, you must have the geometry which is coming from the client. Like, usually our clients provide that in the form of a Revit file or something like that. We, apart from using FreeCAD or other kind of tools, we also use commercial tools for cleaning up geometries, AutoCAD or Autodesk tools. So it's better to have a suitable tool to clean up your geometry before you bring it into CFD. You can do it using FreeCAD as well if you get a proper format for that geometry. You have to combine that geometry and all that. So it's going to be a task in itself, like particularly for BIM kind of a project, right? So it's going to be a task.
Yes, sir. It means I need some external software for the geometry making, and then importing the geometry into the open form.
Yeah. You need to clean the geometry, combine it into one fluid volume, and then bring it into OpenFOAM.
Okay, sir. Okay. Got it, sir.
Yeah. Can design of draft tube be made totally cavitation free using CFD? So, Balkrishna ji, the thing is, I mean, no one would make that kind of a tall claim that CFD would solve every problem. But it can give you an insight as to process-wise what is happening in that draft tube. Sometimes it can be solved, but it depends on the constraints of that particular thing. So I would not say that CFD would solve that problem, but CFD would help you solve that problem some way. So I mean, I would look at it in a way that what you cannot predict analytically or in any other sense, CFD will give you an insight into that kind of a problem, and it should be looked upon like that. Mesh is one of the main part of any CFD. How to solve any path is there. Plaban saying, can you elaborate on that question? You can take it. If you can unmute yourself and ask.
Yeah, hello.
Yeah. Hi, sir.
Yeah, this is Balakrishna here from Goa Engineering College, Goa, Pharmagudi.
Great. Tell me.
Yeah. No, I just wanted to know how do you validate the model, especially for draft tubes? I mean, is it possible to get the data at certain points just to validate the flows?
Yeah, usually, I mean, the kind of problems we come across, sir, they are unique in nature. So the only way to validate them is to construct a physical model which is comparable of a comparable scale of comparable physics, and then get that data from that. In absence of that, what we do is we validate our models on a simplified case, for which there is data in literature, for which there is some data which we can verify analytically. We do that kind of a thing and then extrapolate that model on a complex geometry. That can be done, but you have to look for your particular application. You have to look for what is a simple problem that is solved in literature. You can build a model around that. You can check whether your model is matching with that kind of a data, and then you can extrapolate that model on a complex case.
Okay, sir. Thank you so much.
Yeah.
Also, I just wanted to know if geometrically similar sized model could be used as for experimental setup, just to get the validation model of a smaller size. Is
Yeah,
it
yeah. I
done
mean, experimentally, usually it's very difficult to go for the same scale. Like it becomes a whole full scale project. Sometimes it happens like particularly in civil, sometimes it happens that the structure is already constructed. There is some flow is already happening there, and then there is a problem. So we can take that whatever structure is there, replicate it in a CFD model, and then match it. But in some cases, if you are doing a design or something like that, it's not possible. So you have to go for a scaled model. Scaling also, certain phenomena can be taken care, but in our cases, particularly aeration sedimentation has a problem with scaling. So I would be cautious on that. So the kind of problem you are looking at, what kind of draft tube you are speaking of, sir?
No, no, I was asking a general question because cavitation is a phenomenon attached to draft tubes, how much ever
Yeah.
you design.
Yeah.
So I was just asking, meaning using CFD and to validate the draft tube, it becomes a bit of difficulty. So I just wanted to know your views on that.
Yeah. So I mean, if you have to ask me how would I have approached it, I would have done a lab setup where the cavitation is happening, replicated in CFD, see the cavitation is happening or not, or whether I'm getting the cavitating pressures or not. So in CFD, there are multiple ways of doing cavitation. So you can do a full multi-phase problem where the cavitation is, you can actually see the cavitation, or you can just test the pressures and find the cavitation potential there. We go by cavitation potential. So you can do that. I mean, you can set up a small problem in a lab, set up a similar problem in CFD, get your physics right, and then you can extrapolate it to a larger problem. So that can be done.
Yeah, sir, in continuation to that, no, I just wanted to ask you one more question. See,
Yeah.
when we do pump testing in the laboratory, especially for the NPSH R requirement, NPSH required.
Okay.
So generally we used to do it in the laboratory and do the tests by varying the suction height.
Okay.
Now, can this same be replicated by using CFD
Yeah,
by
yeah.
knowing? Yeah.
Yeah,
So
I mean, but it's just that you have to convert the pressures properly. Sometimes, like for particularly for pumps, I mean, we measure in sometimes head or like the column of water. We have to convert that into pascals or something like that for units. Once that is done, you can replicate that in CFD easily.
okay, sir. Thank you very much.
Yeah,
Thanks
thanks
for
a lot.
answering.
Yeah. So Plaban Sen, can you unmute yourself and tell me? We have, I think, only 1 minute left. You can take that last question. Mesh is one of the main part in CFD. how to solve any path is there. Solve mesh generation for 2D or 3D geometry. So OpenFOAM comes with meshing tools, block mesh, SnappyX mesh. It also has tools to import meshes from other solvers. You can look into it. I think there are some tutorials available for that also. Maybe for someone from FOSSEE can also help you in that meshing.
Sir, just to add on it,
Yeah.
scheduled a detailed session on meshing on day 3. So interested candidates can join that session as well. Thank you.
Yeah, so Sohail Kukian has asked a question, what kind of boundary conditions have I used for air and water? So there is a special boundary condition in OpenFOAM. It's called variable height flow rate inlet velocity. Long name, but it's a specialized condition where you can have air-water interface at the inlet and you can specify discharge. Water will come into the domain, and the velocity at the inlet for water will be adjusted based on the height of the water. That's for the inlet. For the atmosphere, we can use any inlet outlet or zero gradient condition. You can fix phase fraction for you can use fixed phase fraction using fixed value. For outlets, you can use pressure outlet conditions or inlet outlet conditions or zero gradient. It's a different combination for different kind of application. Particularly for these kind of problems, the outlet matters a lot. So you have to try a few things to figure out the outlet. And I cannot cover it here, but that's the most critical thing here for open channel flows. Rajwal Bohra is asking, thank you, sir. It seems so helpful to make disintegration. Which solver would you recommend to use and how we can achieve good result for it? Boundary condition. So for a descender basin, there is a solver which is there. It's called drift flux foam. It's a two-phase solver. One phase is water, one phase is the sludge. So probably that can be implemented, but you have to assume the water surface to be flat. Otherwise, you can go with multi-phase Eulerian kind of an approach for doing that. Have you worked on some erosion case using OpenFOAM? So Sahil Kukian is asking, have you worked on some erosion case using OpenFOAM? We haven't come across yet, but I know a solver for doing that. So it's called SEDFOAM. So SEDFOAM deals with scouring and sediment transport using OpenFOAM. So it's an external solver built for OpenFOAM. You can search SEDFOAM, SADFOAM. That's built for scouring. Is that CATIA V5 geometry can import into OpenFOAM? If you can export it into maybe STL, IGES, a step file, you can import it into Snappy. How to import the geometry into OpenFOAM. So I think I myself have a YouTube channel and I've made only one tutorial there. So there is so there is a video on how to prepare geometry for OpenFOAM, how to split it, how to combine it and all that. So I have made a video on that. You can search for that on YouTube. And maybe FOSSEE will also help you in that demo for upcoming demo formation. Yeah, I think I've covered all the questions. If anyone is, I think we are also out of time here. I did not expect that this to go long. Yeah. Paris, you can take up. Or ma'am, you can take up. No problem.
And
Yes. Thank you so much. So many questions, and you have been so patient. So I'll reply to each and every one of them.
Yeah.
Thank you so much, Mr. Desai.
Yeah.
Thanks a lot for joining, and thanks a lot for this informative session. I mean, a lot of things I think were new to most of the students. I think most of the students might have gone through all these kind of diagrams and actual images that you showed during the presentation. It was really helpful.
Yeah.
Thanks a lot.
Yeah.
Yeah. Okay. So, Nikhil, over to you. So,
Yes, ma'am.
Nikhil Chidla is yes. Hello.
Yes, ma'am. Yes.
Yes. So Nikhil Chidnavis is our team member from the CFD team of FOSSEE. He's also a final year student of PhD. He's doing PhD in IIT Madras. So he's a very experienced person, and the next demonstration session will be handled by Nikhil. So over to you, Nikhil.
Okay, ma'am. So good afternoon to all. So as this session has been, yeah, some question is there or not? Okay. So this session has been taken by Ranjit sir, and he has given the application of CFD. Hello. Okay.
Yes, Nikhil, you're audible.
Yeah. Okay, ma'am. I thought someone is trying to speak up. So.
Okay. So I would request all the participants to kindly mute your microphones. And there might be some background noises that can be hindering the session. Okay, so yeah, Nikhil, please continue.
Yes, ma'am. So this session has been taken by Ranjit sir, and he demonstrated and explained the application of CFD in the water sector. So we'll continue with that only. So let me share my screen. So we'll go. I will going to demonstrate a few cases how we can model it in open form. Whether the screen is visible, ma'am?
Yes, Nikhil sir, it is visible. You can continue.
Okay. Thank you for this. So first case which we're going to see, and Ranjit sir has also talked about it in his session, that is dam brick model. So it is already given in the open form. If you go to open form, let me show you also where it will be, where you can find it. So in my case, it will be in some different location, but you have to go to tutorial section in the open form. And I'm using OpenFOAM 2412. Inside the tutorial, there is one multi-phase folder, and inside multi-phase folder, this interform you can see, and there are lot of flow parameters which is given, like laminar flow, RANS modeling, and LES. So we'll see with some basic case of dam break in the laminar flow model. So this case we can simply copy, and it will be good that you should not run any case in this installed directory folder. It's better to copy it in some other location. Yeah. So coming to this dam break case and this session also. So we're going to see the two-phase flow using VOF model. So in VOF model, we'll actually trying to capture the interface of the two phases. So for the current case, I'm using air and water interface, air and water as two fluid. So we're trying to capture the interface between the two fluids. So starting with the setup. So this I will not go into much detail with, and these things have already covered by Ivan in the previous session. Starting with zero folder, which consists of the boundary conditions or the variable, that is the pressure and velocity. Apart from these two variables, for the multi-phase flow, one alpha is nothing but the phase. It will one additional variable it will going to solve, and the additional equation also it will going to solve. Then coming to constant, which consists of the parameters of the fluid, which has density, viscosity, and even the information related to the mesh, and system folder, which consists of the controlling parameters of the solver, what discretization scheme we're going to use, and the metric solver. So this is the first case, which is called as the dam break model. So this mostly has been used to study the behavior of water column when, or the application of dam break, when the dam will break, how the water will going to behave, how much instability it will going to form. So you can see, so to simulate this, we, as I've already said, this is a established case in open form. So this is the water column, which we're going to initialize in the open form, and the remaining blue section is the air domain. So under the effect of gravity and also the density, how the this water column will going to behave and how the flow will be there. Further moving forward, as I've already said, this is a VOF model, which is used for solving the multi-phase flow. And these are the governing equation which it is solving, starting with the continuity equation and momentum equation. So if you look in this momentum equation, one additional source term it will going to solve. So as we are solving the two different fluid, so one is a continuous fluid which is water. So surface tension will come into effect, and this surface tension force will treat it as a source term in the momentum equation. And to capture two different fluid and their interfaces, this is the alpha equation or the phase equation. So the alpha is denoting the phase of two fluids or two fluid domains. So this alpha equation is the additional equation which this interform solver will going to solve. And to capture the interface between the continuous phases of fluid, this convective term has to be discretized using a different discretization equation, which we're not going to cover into detail. So coming to our dam break case. So this is the setup, which I've already said zero constant and system. So if we'll go inside the zero folder, as I said, it will consist of pressure and velocity. And apart from this pressure and velocity, one additional variable you can see, which is called as alpha. Alpha is the phase. So we're going to see one by one in all these three files. Yeah. Whether the text is visible or should I make it enlarged?
It is visible, sir.
Okay, fine. So in this files, we are defining the boundary conditions which we are defining on the wall. So as you can see from this image, these three walls I have given the no slip boundary condition. That means the velocity at the wall will be 0, and this is open to atmosphere. So same thing we can see from here also. So left wall, right wall, and lower wall has given a no slip boundary condition, and the atmosphere, that is the top wall, has given the pressure inlet outlet velocity, and that means it is open to air. Further, we are seeing the 2D case, so that means it is not going to solve the. Hello.
So you can continue. It was some...
Okay, fine. Yeah. So it will not going to solve the front and back faces. So that's why we have defined it as empty.
Sir.
Yeah. Hello. Okay.
Could you repeat once?
Oh, should I? Oh, should I have to repeat this?
Oh, yes, sir.
Okay, fine. Yes, sir. Okay. So which portion I have to repeat, or should I have to go through all these boundary condition again?
All boundary conditions.
Okay, fine. So if you see this image, so these are the walls, and on this wall, I'm giving a no slip boundary condition. So how to define no slip boundary condition, and what is no slip? So no slip, nothing means the velocity at the wall will be 0. That means the fluid will going to stick on the wall. So either we can define simply a no slip, or we can define a velocity on this wall as 0. So for that, we can also write fixed value, and we can define the value of the velocity as 0. So we are defining, sorry, so I write uniform. So like this also we can define the no slip boundary condition. That means we are instructing, or we are implementing that the velocity on this wall will be 0 for all the time step. Or the second way, we can simply write the no slip, which already this boundary condition has already been coded in the open form. So both ways, in using both ways, you can define the no slip boundary condition. Apart from this, the top region, I said it is open to atmosphere. So because of this, I am defining pressure inlet outlet velocity. That means it will not going to restrict the flow. It will simply allow the flow to move out of the domain. Also, these default faces, that means the front and back faces, which I will going to show when going to develop the mesh. What exactly is this default faces and why we are defining it as empty. Now coming to pressure, so you can see in the pressure, it is written pressure RGH. So RGH is nothing but we are subtracting the rho GH term from the pressure. So in the multi-phase flow, we're going to define the gravity also as a source term in the momentum equation, which I've showed it here also. Yeah. So this is the gravity term, which is act as a source term again in the multi-phase flow simulations. And what boundary condition we're going to define it here. So on these three wall, we have defined some fixed velocity. Even though it is a zero velocity, but some fixed value we have defined on the wall. So pressure will be the gradient of that means the fixed value will in the CFD field. If you are defining some fixed value to any boundary, it is called as Dirichlet condition, and the other variable should be go as a Newman condition. So it will not. We are not providing any fixed value based on the time step and based on the calculation. It will going to recalculate it or back calculate it on each of these walls. And again, as I said, atmospheric condition, it is open to atmosphere. So that's why we are defining it here. The pressure is zero. So it will take it as a gauge pressure. So it is open to atmosphere. Now coming to alpha phase, that is the water phase or gaseous phase. So here we are simply defining because we are not defining any phases on the wall. So that's why we have given zero gradient to the boundaries. And again, it is open to atmosphere. So whatever, if that means it will allow the fluid to go out of the domain. Now coming to mesh or the boundary or the computational domain. So as this is a established case in the open form, so block mesh or the mesh file is already been given, which you can see that vertices has been defined. Block mesh and also the block mesh is worked on dividing the computational domain into various blocks. So based on this, you can define the number of vertex in X and Y direction, and it will create the mesh for you. And here in the boundary section, you have defined the various boundaries or the patch name for the boundary based on the vertex. Based on the vertex, you have defined it here. So we'll see how it will going to create the mesh. So for this demonstration, I'm using OpenFOAM 2412. So first I will source it. Then I will go to that location where I've kept that test case. Now, as I've said, we will require a zero constant system. So what is this zero org? So this is simply a original file. So whatever changes if you want, you are doing in zero file, and if you want to check what is there in the original file, so it's like a backup file for the boundary condition. So you can simply make a zero folder out of this simply by copy paste and rename it as zero. So now this will become act as boundary condition, constant and system. Now we're going to create the mesh using the block mesh. So for creating the mesh out of block mesh dict file, so the command is block mesh, and yeah, so it has created the mesh, and you can see it is reading all the patches also, which we have defined it in the block mesh dict file. Now to check the mesh, whether or the property of mesh, whether it's orthogonal mesh, how many mesh elements are there, how many faces are there, that we can see using the check mesh command. So after running this check mesh command, we can see the total number of cell is only 2268. So it is very coarse. You can refine it by editing the block mesh file also. Then other thing also you can check what is the aspect ratio of the mesh, whether the mesh is orthogonal or not. Those things you can modify and check it using check mesh command. Now to visualize this mesh, we have to create a temporary file which can be readable in Paraview. So I'm using this command touch. You can give any name and then .form. So this is our computational domain, and if you click over here, this surface, one option is there, surface with edges. So it will give you the you can visualize the mesh using this command or this option. So this is our computational domain, and as I was mentioning, that we are not going to solve it as a 3D domain, it is a 2D domain. So that default faces as empty, what we have defined it here. So that means this front face and this back face, we have defined it as empty. So it will not going to solve on these two faces. That means it will not going to solve any equation or any parameters on these faces. So which will treat it, this domain as a 2D domain. Now coming to as I've showed it in this about this water column. So till now there is no water column, or we have not initialized anything. So how we're going to initialize that water column, and how we're going to differentiate that which part of this domain will be treated as water column and rest of the thing as air. So for this, inside this system folder, there is one dictionary or file called as set field. So here we're going to initialize the various phases. So this is the file in which first we're going to define the default field. So here we are considering the default field as air. So alpha phase will going to vary from 0 to 1, where 0 denotes the fully air domain and 1 denotes the water phase. So all over the domain, I am defining it as alpha is 0. So by defining this, it will going to initialize air all over the domain. Now coming to the water column. So it is nothing. So if you see, the water column is nothing but a rectangular box. So for which I'm defining a box with the dimension. So this dimension you can get it, means what is the exact size of this domain. You can check it in Paraview also, or the size of domain you have already defined it in the block mesh dict file. So if you come here, so it will show you what is the exact size of the domain. So based on this domain size, I'm defining the box for the water column here. So this will be the so in this initialization also, it will work as I'm defining only two vertex, so it will diagonally trace it. So this will be the first vertex, and this will be the second vertex. So based on this, after reading these two vertex, it will going to form a rectangular box. So that's why we are defining here the two vertex only, and the field value in this box, I'm defining it as a alpha as 1. So as I've said that alpha is the phase and 1 denotes the water phase only. So using this file, we're going to initialize our flow field. So to initialize it, and also if we'll see the alpha water file that is there in the 0 folder, currently the internal field is 0. That means nothing has been initialized. It is taking a default value of 0. But once initialization will be done, we will going to see some values it will going to show. And also this thing we will going to visualize it in Paraview. So to initialize, the set fields command is there. And after using this command, you can see it is saying that the alpha value of 1 has been initialized to this box. Now if you'll see the same file, we have to reload it. Oh, so this file belongs to the 0.org. So we have to see this file. Yeah. So now instead of internal field as 0, you can see some values it has defined here, starting with 0 and 1. Also, the same thing we can visualize it in Paraview also. So if you load this file in Paraview again, yeah. So now in this drop down box, all the parameters are visible. And if you'll select alpha water, so now you can see it has initialized this water column and the remaining is air. Now for the simulation of this dam break case, we are using the interform as a solver, and the controlling and discretization, we can check it using these files, starting with control tick, FE scheme, and FE solution. So we're going to see quickly one by one all these files. So FE scheme will going to tell us that we can see the equation. So in the momentum equation, which term is discretized using which scheme? So the first one is the temporal term, this DDT term. Second one is convective term, then gradient of pressure, and then the diffusive term. So all this term we're going to discretize using different schemes. So this DDT scheme is the first term, that is the temporal term, which and all this discretization scheme is already given in this open form. So that's why we are simply calling this function by the respective name. So this DDT scheme is the first term, that is the temporal term, is discretized using Euler discretization scheme, which is the first order implicit in nature. Then the gradient scheme is the discretization of the pressure, which we are discretized using Gauss linear. So in this, in the open form, Gauss linear simply denotes the second order central difference, discretization. Then coming to divergence term. So as you can see, there are various divergence or convective term, both are same. So you can see there are various convective term has been defined. So why they are defining this four divergence term? So you can see the first divergence term will be coming from this momentum equation. Now this is also a divergence term, which is coming from the continuity equation, and this is the third term, convective term, which alpha equation will going to solve. So because of this, there are different divergence or convective term, and which are discretized using different discretization scheme. Now coming to Laplacian term, which is the diffusive term. So this is this fourth term, in which the viscosity of the fluid is defined. Then coming to the FE solution. So each term, that is alpha, pressure, and velocity, will form a matrix. So how we're going to solve this matrix, using which solver or which iterative method we'll use for solving this matrix is defined here in this file. So we're not going into detail of this matrix solver. So we can simply say that it is something like we have already know the different matrix solver, starting with Gauss-Seidel method, conjugate gradient method. So these things are all only defined it here. Now coming to the control dict. So in control dict, we're going to call our solver, that is interform. We're going to define that the simulation will start from what time, and we can also change this time. So as we are initiating the simulation, that's why we have defined the start time as 0. End time we can define. So we are running this whole simulation for the total time of 1 second with the time step of 0.001. So this delta t also we can keep as fixed, or it will going to vary based on our simulation. So that's why they have defined as adjustable. Not going to be remain constant. It will going to vary as per the convergence. Now coming to write interval. So after every 0.05 second, it will going to write, or it will going to save one file as a data file. Now in which format we are saving our data? So that we have defined it here, that is the ASCII format. You can save all your data, or you can save the files in the binary format also. Now current number, we are defining it here, that is the maximum current number. So if we are defining the maximum current number, so the simulation or delta t will going to calculate based on this maximum current number. So this is the basic overview of this dam break case. Now we'll going to run this using interform solver. So I will simply write interform, and if I press enter, it will start running. And as this is a very coarse mesh, so it will not take much time to complete our simulation, and it has already completed also. Yeah. So as I've said, based on the write interval, that it will going to save after every 0.05 second. So we can see that at the interval of 0.05. So this is the first file, that is 0.05 second. Then after each and every 0.05 interval, it has saved these many files. So after the completion of this simulation, we can visualize it also in the Paraview. So for that, we have to refresh it so that it will able to read all these time steps. Now you can see instead of showing 0, it is showing the maximum of 19 time steps. So to see the animation of this dam break case, we can simply play it, and you can see how the dam breaks and the behavior of the water. So this is how it will going to behave after the breakage of this water column. So that only I have showed it here in the animation form. So this image you can save it also using this screenshot option, or you can form an animation using this save animation option. So it will give you a lot of option whether you want to save each and every time step as a PNG file, so that many images it will going to save, or you can directly export it in the MP4 format. So if I'll save it, it will ask for whether I want this transparent background or not, and it will start saving. And this animation you can use it for the later purpose also. Now coming to the velocity, so this is only showing the behavior of alpha phase. Now how the velocity will going to behave? So simply we have to change from alpha water to velocity or pressure. So which will going to show how the pressure and velocity variation all over the fluid domain. Further, you can see the streamlines and velocity vector also in this by taking a slice. As it is a 2D domain, so no need of taking slice also, but it's better to take it. So there is an option called a stream tracer. So if I'll switch it on, so you can see a line. So it is denoting that it will going to plot the streamline across this line. Either you can use this option, or which is the default, or you can change the location of this line. And if I apply this option, you can see some streamlines it has formed. Yeah. And you can change the density of this streamline. So there are various options given in this stream tracer option. So you can see the maximum length. If I'll decrease the maximum length, it will decrease the length of the streamline given here. Also the number of time steps or maximum steps. If I'll increase, it will increase the density of this. Apart from this, if I want the streamlines in some specific areas, so we can use this seed type. So earlier it was line. Now I'm changing it to point cloud. So if I want streamlines in this region only, so I will go to point cloud. A point cloud, if you see, will appear, and I only have to move this point cloud to that specific location. And if I apply, it will give me the streamline at that location only. And after that, I can increase the maximum length. to further crowd that area. Also, I can increase the radius of this point cloud, which is given here. So if I define it as 0.1, you can see the radius of this sphere will increase. And the streamlines will be more visible. So like this, you can control the streamlines also. Further coming to the post-processing. So you can define some probe location in this flow domain to observe the dynamics or the instability of the flow domain. So this was all about this first case, that is dam break case. If you have any question, then you can ask. Otherwise, we can move towards the second case.
There is a question in the chat box, Vicky.
Okay. Okay, so Aditya, related to the y plus value. So first, you have to calculate the y plus value. There are many online tools, sites available to calculate the y plus value. And in the block mesh option, let me show you. So in the block mesh option, so currently I've given the grading as 1 1. That is that means it is a equal spacing between all the cell all the mesh elements. So by changing this, you can vary the y plus value or the grading also. Yes, we can apply the grid adaptive technique also in this open form, which is called as adaptive mesh refinement, AMR. Okay, so currently I don't, for this session I don't have, but tomorrow one more session is there on multi-phase. In that I will try to show you how the adaptive mesh refinement actually works. So if no other questions are there, ma'am, can we move towards second second session or second case?
We can go ahead. Yeah.
Okay. Okay. So the first case I have shown is already given in the open form tutorial. Sorry. We can use, but for the VOF technique, solid particle, this thing will be little difficult. But in case of VOF method, but for this kind of modeling, you can use Eilerian approach, where you will not able to capture the interface, but as a bulk effect, you will able to visualize it. And this kind of approaches has been widely used for boiling or even for fluidized bed kind of thing. So in fluidized bed, there are two phases we used to define. That is one as a solid particle, bed of solid particle, and other as air or water. So that tutorial, one basic tutorial is already being given in the open form that you can explore. Okay, so we can start the second case. Yeah.
If the audience wants some break, like of 2-3 minutes, can we give? If they
Yes,
want.
ma'am.
So,
Okay,
so
ma'am.
do you
If
want a break between these two cases? Maybe 2-3 minutes, just water break or something. If you want, you can just raise your hands in the chat box. Otherwise, we'll move ahead with the next case.
it seems like they want, ma'am. Yeah.
They want, yeah. Okay, fine. So should we take 3 minutes or maybe 5 minutes break? Will the
Fine,
time
ma'am.
permit?
So we can start at 3:50.
Yeah. So it's 3:45 by my watch now. So 3:50
Yeah.
we will start. We can take a break. It will be good for them to absorb the two different cases.
Okay, ma'am. Okay, fine.
Yeah. Okay, fine. Okay, it's 3:50 now, Nikhil. I think we can start.
Okay, ma'am. Yeah, okay. So we can start the second case in the demonstrative session. Screen is visible, ma'am, right?
Yes.
Yes.
Okay. Okay. So the first case which I've showed was the well-established case given in the open form tutorial. The second case is the modeling of wave, which I'm taking from the case study repository of the FOSSEE. So that case you can find it in the case study section. If you'll go to FOSSEE website under open form section. So under this completed case study, you can check this. Yeah, you can check this case. In this also the solver used is open form. And in this it is shown how to model the wave and how the interface between the air and water will going to behave. So you can simply download it and go through it. And meanwhile, I will explain all about this test case. So this test case is case number 129. So this test case I have already downloaded. So we can go through this test case one by one. So let me show you. So this test case is something like this. The bottom wall is no slip condition. This red zone is the continuous water zone. The blue one is the continuous air zone. From inlet, we're going to define a wave type boundary condition, which we're going to see how to define it. And this is the outlet condition. And again, the atmospheric condition is open to atmosphere. Yeah. So this is the computational domain, which I've showed just now. Yeah. So coming back to the test case. So again, in this zero folder, these three files will be there: velocity, pressure, and alpha phase file. Second will be the constant folder, which will consist of G, that is the gravity, transport properties, and turbulence properties. Now, apart from these three files, one more file you can see, that is the wave property file, which we'll going to explore after a few seconds. And polymesh file. So the polymesh folder will consist of all the details of the mesh, starting with boundary, phase, neighboring elements, and the number of points which are available in the mesh. And the system folder. So coming to the zero folder, we're not going to spend much time on this zero folder because most of the thing I've already explained in the previous demonstrative session. But I was talking about we're going to model the wave, which I've already shown a schematic of the wave in this slide. So at the inlet and outlet, so at the inlet and outlet, instead of any fixed value velocity, here we have defined the wave velocity, and this boundary condition is already been compiled in the open form, and what all parameters we're going to consider, we'll see. Then at the outlet, again, it is wave velocity. Now, the back is nothing but the back and the ground. Ground is nothing but this bottom one, where I have defined the no slip boundary condition. So that's why instead of giving the no slip, we can define the fixed value as 0. Now the top, as explained, is open to atmosphere. So that's the pressure inlet outlet velocity is defined. Now, similar to velocity, wherever we have defined the fixed value, we'll define the gradient of pressure at that patch. So that's why this fixed flux pressure is defined. And on the top wall, we have defined the pressure as 0. Now coming to the alpha water. So in this file also you can see in the internal fields, the default value has given us 0. That means it is not yet initialized. And apart from that, here also at the inlet, the wave alpha, that means using the pre-compiled boundary condition of wave alpha, it will going to take some value for implementing the wave condition. So this was all about the boundary condition. Now coming to the constant, we'll see one by one all these files. Out of which three of these files, that is transport property, G and turbulence property was same as that was given in the previous case. So in this we have defined G. So there are three, as G is a vector quantity, so that's why Gx, Gy, and Gz we have given here. So the actual geometry is in the Z direction, so that's why the gravity is defined in the Z direction. And the other two values is given as 0. But it depends on you whether how your geometry will going to be. It can be you can define gravity as per your geometric detail. Now coming to transport properties. So as I've said in the transport properties, the viscosity and density of each phases will going to we have defined, or based on the fluid requirement you can change it also. But for this case, the two continuous phases are air and water. So the transport model we have defined as Newtonian. Nu is the kinematic viscosity and rho is the density. Similar to this water phase, for air phase also we have defined the kinematic viscosity and density. Now apart from these two parameters, sigma is the surface tension of the fluid medium, that is the water medium. So we have defined it here. Now coming to turbulence property. So the simulation type, as I've showed in the earlier case, that we can do this kind of simulation using Rans modeling for laminar also and for the LES. So this simulation is performed using laminar model. Now coming to the wave properties, which is actually being used for implementing the wave inlet condition. So you can see here it is reading we are defining the inlet patch. Now on which phase we are going to define the wave motion. So that's why we are defining alpha as alpha water. Now there are various models based on which the wave nature will be dependent on. So that you can explore further If you'll simply
Nikhil,
search.
I'll just interrupt once. So
Yes, ma'am.
actually, our team has posted the online attendance form for the second half of the day one. So I would request all the participants to please take 1 minute break and post your attendance. And then we can continue.
Okay, ma'am.
We can pause for say 1 minute or 2 minutes. So that all the participants can just fill up the attendance form.
Okay, ma'am. Fine.
Yeah, once you are done, you can just type in the chat box. Or else you can not type also. We'll give you say a couple of minutes and then we'll go ahead, continue.
Nikhil, you can continue. Most of them have typing done.
Okay, so I will continue with.
Yeah.
Okay. Yeah. So coming back to this wave modeling case. So how the wave property will be dependent on. So there are various wave models which you can further explore. If you simply type wave properties open form. So this user guide wave modeling, you can check there are various models given here. So you can do trial and error kind of thing, how the wave will going to behave by using different models. So for the current case, we are using Stokes one wave model. Now, wave height we have defined here. So how it will going to decide the wave height? So after the initialization, suppose this is the half h by 2 height. So from here, how much it will go up and down, that we have to define. Not from the origin, but from the interface. So that height we have defined. Ramp time is nothing but after the start of simulation, after how much time it will going to start implementing this wave type boundary condition, and what is the total time period of this wave. So all these things we have to define it here. And similar to that, in the outlet, we are simply defining that it will allow the wave to go out of the domain. Further, in the system folder, these things I have already explained what is control drift, FE scheme, and FE solution. And similar to this, first we have to initialize the two phases in the set field dict file. So here also, the default phase we are defining it as 0, that is the air phase. And then here we are defining a box, and in that we are defining that the continuous phase will be water. So using this set field, we are only distinguishing the two phases, but not the wave. So wave initial will start using that. Wave modeling will start to implement using that wave property boundary condition. Further, the earlier case I have showed was using a single processor. This case we can see how we can run any case using a multiprocessor. So for that, the decomposed pardict file is available. So in this, we can define the number of processor or number of subdomains. So here I have defined 4. So which means the whole geometry or the whole fluid domain will be divided into 4 subdomain. and each processor will going to solve only that much fluid domain. And based on the system, you can increase or decrease this number of fluid domain. Also, instead of running all the command one by one, we can keep all the command in a single file, and that file we can use for reading or we can use for the simulation. So you can see for decomposing the domain, we are using this decompose file. For initialization, we are using set field file. Then for running the simulation, so this get application, that which means as I've showed, let me open the control dict also. So here we are defining the solver name that is under the application, which is interform. So it will going to call this solver using this get application command, and as we are running it in solver, parallel, so you will going to see 4 processor folder it's going to form, which I am going to show. So once the simulation will be over, we have to reconstruct. Reconstruction means we have to get the information from all the 4 or 5 whatever subdomains you have divided your fluid domain or fluid section. So we have to take the information from all these processor and clubbed into one. So for which we are using this reconstruct par command. So for running this is now, instead of writing all the command in the terminal, I'm simply using this all run file. So as you can see, this file is already been given. So for running this file, /all run, if I press enter, you can see it is it will start showing which command it is running. And as I've said, that we are dividing this whole fluid domain into 4 separate subdomains. So that's why these 4 processor files it will going to create, and inside each processor file, it will going to solve for all the time steps for that much fluid domain. Yeah. So once it will complete, I will show how it will going to behave. Also, you can see that some log files it has created. So you can see using this log.interform how much time or how it is running in all the iterations you can visualize it here in the terminal. So for that, you have to write this tail -f. You have to call this file, and if you press enter, you can see all the iterations which are going on. So as it will take time to complete the simulation, so I will only run it for a few more seconds, and after that I will show the animation which I've already prepared. Better to stop. So now if you'll see, I've interrupted the simulation in between. So it will not going to run that reconstruct par command. So if you are interrupting this whole process in between, so you have to manually write this command reconstruct par. So it will take the information from each of this processor file and create a time step outside of this folder. So for now, if you'll see, only 0 folder is there and no other time step is visible, even in this also. So once I will start reconstructing, you will able to see it has started reconstructing all the time steps. And here also you will able to visualize it. And this time step only we are going to use for the visualization in Paraview. So once it will be completed, I can visualize it in Paraview. Yeah. So after the completion of this reconstruct part, now we can visualize it in the Paraview. So as I've said, we have initialized this fluid domain using the set field file. So that's why there is, instead of showing any mesh wave implementation, it is only showing the 2 phases. And we're going to implement our wave type boundary condition using that wave property file. And in that wave property also, I have defined the ramp time. That means after 0.3 second, that boundary condition will going to implement. So you can see from here that at 0.1, we are not visualizing any wave in this domain. Even at 0.2 second, we cannot see, but at 0.3 second, you can see some depression is coming, and then it will start to implement the wave. Yeah. So now you can see some sinusoidal variation is coming in this interface, and that's how we have implemented the wave. So anyhow, it will not going to move further because I have not run this simulation for enough time. So I can simply show the animation. So if you'll run it for the enough number of time steps, so this kind of wave behavior you will able to visualize. So this was all about the second case. If you have any question, then you can ask. Okay, so decompose par means we are decomposing the whole fluid domain into different subdomains, and reconstruct par means whatever we have solved into different processors, we are reconstructing it into single time step file.
উনিশে ম্যারেজ হল আছে মানে তোমার সেন্ট জেভিয়ার স্কুলটা না তার অনেকটা
Yeah, so for further clarification, we can visualize all the.
Hello.
Yeah, hello.
Actually, I have one question. In the constant file, as you have said, the wave height that is related to the first, means initial height of the
Yes, sir.
water.
Yes, initial height of the water. Yes.
Okay. Thank you. Achha, wave period means this is imposed.
Yes.
Okay.
Yeah, so I was saying that we can visualize the all the fluid subdomain So the file we have created here, right, fluid dot form for the visualization. So if we'll simply copy this file inside this individual processor, we can visualize the flow domain, subdomain also. So I've kept it here. Yeah. So you can see if I'll compare. So I have divided this whole fluid domain into 4 different subdomains. So this is my whole fluid domain, and this is a 1/4 part of it. So the processor 0 will going to solve only this much part till here. You can compare it.
Nikhil, you can on the left hand side, no, in the column under skip 0 time, there's a reconstruct case option. You can switch that to decomposed case.
Okay, fine.
Yeah, it will better help visualize the whole domain when it is broken down into multiple domains.
Okay, fine. Okay, fine. So this is the whole idea of decompose thing. So you can see it is only solving the 1/4 of it, which will speed up your simulation if your total number of mesh elements are very high. I hope this is clear.
Mr. Ajit, Akhil, Venugopal, all of you have raised your hands. Do you have a doubt?
Okay, if there are no further questions, you can explore this test case which is already available in the case study repository of FOSSEE. And if any doubt will be there, you can ask in the next tomorrow's session also. Or even there will be doubt clearing session, right, in the end of this workshop. In that also you can ask.
Yeah, we have like Nikhil, are you done now?
Yes, I am done.
So we can take up the questions now as well. And we were thinking of holding a simple tutorial case so that people who are new to OpenFOAM will at least understand a bit. Just a basic,
that will be
like an icofoam case.
Yes.
So for people who are facing any issue or have not understood anything, you can ask us your questions. Then once that is cleared, we can move ahead with the simple case.
The case. Okay, so for this, Aditya sir, so for letting the wave to go out of the domain, for that only we are defining the outlet boundary condition, which I can show it again. Let me share my screen. Yeah. So here in the outlet, we are defining the wave velocity as 0. And this wave velocity will going to read all the properties from this wave properties. So here in the outlet, we are simply defining alpha water. So that means it is allowing only the wave to go out of the domain. So it will be better to download this case and explore. And if some doubt will be there, you can ask.
Okay. So,
okay, it seems like even no other further questions are there. So you can start the.
Okay. So can I get a quick head count of how many people are new to OpenFOAM? Like haven't tried anything in OpenFOAM till date. You've only done the installation. Okay, we've got 3, 4, 5. Okay. So in half an hour to 1 hour, we'll just take a basic session on the case structure and what are some of the important things to just see while doing a simulation in OpenFOAM. Okay. So I'll share my screen. Just give me a second. Okay. So is my screen visible?
Yes.
The font is visible, or should I increase the size a bit?
It's okay enough. If there are any changes in the code, we can see.
Okay. So now, once you've done your installation, most of you must have tested out whether your installation is working fine. For those of you who are facing some issues, you can always email us and we will try to resolve your queries in the email itself because we passed the installation phase. So now when you first when you're starting with OpenFOAM, the very first case we always tell people to learn is your cavity case. So if you're going for OpenFOAM 9, I'll show you for OpenFOAM 9 and for 2412, where can you find the tutorials and all. So for OpenFOAM 9, you have the OPT folder. Within OPT, you have OpenFOAM 9, and under OpenFOAM 9, you have tutorial files. Okay. So this is where you will have all of your base tutorials saved. Once you install, then you can just copy paste any of these tutorials into your run directory and modify it according to your case. So for our case now, we will take the incompressible tutorial. In incompressible, we have something known as icofoam. Icofoam is just your incompressible foam solver. So you have your incompressible solver. And within this, we have the cavity case. And again, inside that, you have another cavity case. So see, this is your base case, zero constant system. Okay. So let's copy this particular case into our run directory. So we'll go back to home and in that OpenFOAM, and then you copy it into OpenFOAM 9. Now I have multiple versions. That's why it is showing those additional files. But if you have just installed it first time, you will just have one particular file. Okay. So don't really bother too much with how many files I have and how many are there on your system. It keeps changing every time. So let's paste it over here. Okay. So I've pasted within FOSSEE. So we have this cavity case. And now we have, as I said, in the very first PPT that we have a base that is zero constant system. Zero is where you will have your initial boundary conditions.
Ivan sir?
Yes, yes.
There is a request to slow down a bit.
Okay, okay. Okay, I'll go slow. Okay. So have you all understood till copying and where your tutorial files are saved? Just give a thumbs up. Oh. Paris, could you let me know?
Yes. As of now, no one has said anything.
Okay. So I'll show the tutorials also where they are. So once you open your Ubuntu on the left-hand side at the very bottom, you have Ubuntu 2204. So you can open that. And for OpenFOAM 9, you have the OPT file. Within OPT,
I would request everybody to please mute yourselves, mute your audio. Some disturbance is coming from somebody. Gundagala and Sai Dulu, I can read the name. Yeah, thank you. Thank you so much for muting yourselves. Okay, yeah, please continue, Ivan. And if you have any problem, you can just raise a hand and then we can go slow also. There is no problem.
And in this particular session, if you have any doubts, you can unmute yourself and stop me anyway, because we are not really strictly following any timetable right now. This is just an open session so that you are able to understand the basics of OpenFOAM at least, because the upcoming workshops, we won't really go too much into the basic. We expect you to understand or know some level of CFD and OpenFOAM. So those tutorials and demonstrations are kept that way. So that's why we're taking this session now so that we don't have problems in the future. Okay. So as I was saying, in Ubuntu, you have your OPT folder. Within OPT, you will have OpenFOAM 9. Within this, you have your tutorial folder. Okay. So in this tutorial folder, you will have a number of tutorials. So there are your basic tutorials, as you can say that in the morning, what we did, scalar, transport, foam, and all those. So those are your basic. Then you have some combustion related solvers as well. So for people who are asking whether you can do combustion in OpenFOAM, yes, you can do combustion. You have multiple solvers. You can always try these. And in OpenFOAM 9, there are a few. But when you are going with OpenFOAM 2412, there are multiple options you have in tutorials as well as solvers. That's why we've told you to install 9 and 2412, because if you want to do a little bit more complex simulations, we always prefer 2412 because it has much of the solvers, and those solvers are a bit stable compared to OpenFOAM 9. So in OpenFOAM 9, we will first copy an incompressible solver or a tutorial. So under incompressible, you have a number of solvers again and tutorials. So we will take the icofoam. Okay. So your incompressible foam. So we have icofoam. Under this, you have a cavity folder. And within this, you have one more cavity folder. So we'll be copying this particular cavity folder. Okay. So I've copied this already into our run directory. So you can go back to home, your name, OpenFOAM and OpenFOAM 9. And within this, you have your run directory. Okay. Now in run directory, I have made multiple folders. So I'll just save it into one of these folders. So over here, I have one case, FOSSEE, and inside that cavity. Okay. So now in this cavity case, as I mentioned previously, you have three main folders, your zero, constant, and system. Now in your zero folder, whenever you copy, you'll have these additional zone identifiers on Windows. If you're on Linux, you won't have this problem. So you can delete those zone identifiers or you can leave them as it is. It won't give you that much of a problem. Okay. So in your cavity case, you will have zero, constant, and system. Your zero will have your initial boundary conditions. So you'll have velocity, pressure. If you want temperature, you'll have another temperature file. If you have, like we had scalar 1, scalar 2, in multi-phase, you saw that we had a special file for air, for water. So depending on the tutorial you're trying to solve or the case that you have, these initial boundary conditions will change. But for the very basic cases, you will always have your velocity and pressure. And for some cases, temperature. So these three files are the very basic ones. Okay. So you will have these files. So let's open one of these. So you can, for people who don't have VS Code or any of the thing, you can open it in Notepad. It's not a problem. Okay. So we'll open this one in Notepad. Okay. Yeah. So again, in Notepad, once you open, as I mentioned in the programmer's guide, you have the dimensions. Now, if you're starting off, you don't really need to pay that much attention to the dimensions. You just need to make sure that they correspond to the proper unit that you have. So this is where you have your dimensions. You can always refer to the programmer's guide. Like, as I said, first one gives you length, mass, time, all of those things, temperature and all those things. Then you have your internal field and you have your boundary field. Now your internal field, you can think of it as a flow inside. Like if you have a box, you have a flow already initialized and kept. So now now currently you will have an internal flow of 0. But if I were to change my moving wall, now suppose on top we have like in this particular case, I'll draw it and show you. Let's open Paint. So in our particular case, the one that we've copied now, the cavity case. So what is happening in this case is you have, this is your domain, okay? You have walls, this part, and this part. These three are walls, okay? It's a 2D case, so you don't need to bother that much in the Z direction. So these three are walls, and the top one is a moving wall. So you will have a velocity. It is like, you can think of it as if you have a box and you are sliding the lid, like sliding the lid in the x direction up to infinity. So this is what this case is actually doing. You have this top lid that is moving in the x direction, positive x direction. Okay. So ideally, when you have a case like this, you would have some flow, since only the top is moving and these three are walls. Once you reach this side, it will hit this wall. Once you reach this side, it will again hit this wall. It will hit this wall and it'll keep circulating within this. Okay. So this is the flow that we're going after in this particular tutorial. So by understanding how this flow is happening, you can see that in a boundary field, we have moving wall and we have fixed walls. And you have the front and back. Now, since it's the 2D case, we are leaving it as empty. So in the moving wall, we have given the value fixed type. Now Nikhil has explained most of the boundary condition and boundary types that we are using. So we need not go too much into detail. So fixed value in simple terms is just you're giving a value in the X, Y, Z direction. Okay, so you'll have a uniform field and you have the coordinate system. So we are giving the value in the X direction, positive X direction as 1 meter per second. Okay. And at the fixed walls, we are giving no slip condition, meaning that if anything were to hit that wall, closer to the wall, it will stick. That is like in your real world scenario. Closer to the walls, you will always have a boundary layer forming. So for those reasons, we use no slip condition. But in certain cases, you might want to use, say, slip condition for it to act like an artificial wall that does not exist. It's just there for like a channel case. In those, we usually use slip condition so that the walls do not affect anything of the flow. Or you can use the slip condition, no slip condition, which will basically form your boundary layer. And depending on the case, you can change these. Now, if I were to make it an open domain, I would use symmetry conditions or zero gradient. So those are your far field conditions. So again, depending on the case that you have, you can change these. We need not go too much into detail for this. So we have a velocity in the positive x direction according to this, okay, with 1 meter per second. Now, this is your velocity. Okay, I'll keep this open. Then we go to our pressure. Okay, yeah. So now in pressure, again, you can check the dimensions. Over here, it is mentioned internal field, uniform 0. And in the moving wall, we've kept everything to 0 gradient. Okay. Now for pressure, usually we do not go too much into it because it's a velocity driven case. If you were to have a compressible or you're looking after shock waves and all of these parameters in which your pressure, temperature, velocity, all of these parameters are really important. In those cases, you will be changing all of these flows, all of these parameters. But in the cavity case, it's a very simple case. You don't need to really change anything. You can, if you want to just learn something about OpenFOAM and you just want to start off, you can try modifying this cavity case and you can try increasing the velocity and see what exactly happens. It's a good test to understand what exactly is happening in your domain. So this is your velocity and pressure, two of your initial boundary conditions in your 0 folder. Then coming to the constant folder, you will have the transport properties. Now, ideally, your transport properties will look something like this. Okay. Right. Yeah. So ideally, it will look something like this. You just have your new parameter, okay? Your kinematic viscosity. Most of the simulations, if it is a flow simulation, will just ask you your kinematic viscosity. Certain cases might ask you your dynamic viscosity and some additional parameters. Like in our case, when we were solving for scalar, we required to give the thermal diffusivity, thermal conductivity, all of those parameters. But in these pretty simple cases, you just have to specify your viscosity of your fluid, and then you can move on. Now your viscosity, you can base it on your Reynolds number. So say if I were to run a Reynolds number of say 100, so I would change my velocity or I would change my viscosity. So either of those, you can tweak these to get your Reynolds number or the range of Reynolds number that you're looking for. Okay, so this is your transport properties. And if you were to run a turbulent case, you would have another file that would be turbulent properties or momentum transport properties. Those will give you just additional parameters of whether you want to switch turbulence on or off. That's the only thing that's going to do. And in that, you can also specify which turbulence model you want to use. Now in OpenFOAM, we do have the RANS model. You also have URANS. You have multiple. You have K omega SHT, many K epsilon also you have. So depending on what you want to solve, you can always incorporate those files as well. And then we have our system folder. Now in system, we have the block mesh, control dict, FV schemes, and FV solutions. So let's open one by one. So we have, okay, we have our block mesh. Make it full screen. So in block mesh, the very first line we would have is convert to meters. What this does is it is just going to divide all your values by a factor over here, whatever you mention over here. So if I were to keep this as just 1, any values that I've put over here, it will just be 1 meter. If I were to put it as 0.1, it will divide everything by that number. It will basically multiply everything with this number. Okay, so let's keep it as 0.1. Vertices, now we have many workshops on block mesh itself. We also have spoken tutorials. So you can see those to better understand how to define a block and how to create a block or a mesh using block mesh. So to make things very simple, we'll just draw it on paint over here. Okay. Yeah. So now we have the points 0.0, basically 0, 0, 0. This is your XYZ coordinate. So let's make a new. Okay. So at say this is my XY coordinate. Okay, this is Y, this is X. So we are putting 1 point at 0, that is over here. Okay. So we have 1 point over here. This says 0 at your origin. And the next point is at a distance of 1 in the X direction. And the next one is at a distance of X and Y. The next one is only at a distance of Y. So this is one, you've made 4 points, and then you join these 4 points using this hex coordinate system. Okay. Now in block mesh, you would require to make a proper hexahedron. Okay. That means you need to have 4, no, not 4, you'll need to have 4 points in the front, 4 points in the back. That makes a total of 8 points. And you would need to have in total 6 faces, correct? So you would have something like this. If you see these coordinate systems, you can just correlate them with this particular drawing. So so over here we see that this first front point, or the back one, you can say, okay, we'll take the back one. The back one is the origin. So we have these particular 4 points that we had made. And then with the depth of say 0.1 in the Z direction, we've put these 4 points. Now we've mentioned this 0, 1, 2, 3. Okay, so these correspond to the coordinate system that you have mentioned over here in your vertices. So you can say this as 0, this is 1, this is 2, and so on and so forth. Okay, you get the idea. So over here, what we're doing is we are mentioning that these points have to be or like put in this particular order 0, 1, 2, 3, 4, 5, 6. That makes up one block. Okay, so this is 0, this is 1, this is 2, this is 3. Then you replicate or mirror the exact same thing. So corresponding to 0, you'll have 4. Here you would have 5. Here you would have 6, and here you would have 7. So that makes a total of 8 points. Okay. Now, once you're done mentioning your or defining your whole block, then you move on to the cell size. You're going to define the cells within that block. So over here, you have again the XYZ coordinate. Everything over here follows the XYZ coordinate system, okay? Leaving the boundary part, okay? So over here, you would have X direction cells, Y direction cells, and Z direction cells. So over here, we specified 20 by 20, and in the Z direction, we only want one cell because we are just solving for a 2D case. If you're solving for a 3D case, you will mention this over here also. And simple grading as 1, 1, 1. Now your grading is similar to inflation, like how we use inflation in ANSYS. So if I were to change, we can change this as well. So first let's keep it at default. I'll show you the mesh itself. Okay. So might as well do that right now. So let's say we open in terminal. OF9. And first I do a block mesh. Okay. So my mesh is done. Show you in Paraview. Okay. So this is a simple geometry. Okay. As I showed you, in your X and Y direction, we have 20 cells, and in the Z direction, we just have one cell. Okay. Now, if I were to change this grading, so say in the X direction, I want a grading of 2. Now, your simple grading is just a ratio of your last cell to the first cell. So when I type over here 2, it means that it is your last cell to the first cell, right? So that means my last cell will be 2 times as that to my first cell. Okay. So it's a ratio. So if I were to save this and again do block mesh, parafoam. So you see, my last cell is 2 times of my first cell. So depending on the ratio or how coarse or how fine you want your mesh, you can change that parameter. Okay. So let's keep this as 1. Now there is something known as multi-grading as well. If time permits, I might show you that as well. Multi-grading is handy for cases in which you don't want to split your domain into multiple blocks, because now see, if you were to, now for our particular case, we know that at the walls, we are going to have some boundary layer formation and all. So might as well increase the mesh closer to the walls. But if you do that, you would have to break down the domain into multiple blocks. Okay, if you're doing simple grading. But with multi-grading, what you can do is, again, back to the drawing board. So suppose this is your domain. If you were to make a mesh closer to the wall, now with this particular simple grading, all my mesh went towards the left, right? So here we had fine mesh, and then here it became coarse. But with multi-grading, you can define, like you can split this entire line or your entire X direction into multiple parts. So I can say that I want in this corner, I want fine mesh. In this corner also, I want fine mesh. And as you move towards the center, I want it to be coarse. So multi-grading gives you that ability to manipulate that whole block as per how you want it. And you can use less number of blocks because of this. So that is what your multi-grading is there for. We have a specific tutorial on that as well, so you can always go and check that out. Okay. Then once you are done, yes. Does someone have a doubt?
Actually, I was seeing some questions in the chat box. I'm not sure whether we have taken that.
Okay, Paris or Nikhil, if you are able to read those chats, you
Nikhil
can just let
has
me know.
left, so Paris is here.
Okay.
Yeah, Plavan Sen has asked one question. Please explain 1 second difference, decompose P par and reconstruct par. Was it taken?
Yes, Nikhil has taken that one. Yeah.
Okay, fine.
Okay.
Yeah. Okay. So Paris, please keep checking the chat box. I'm also doing that in case we miss something. Okay. Yeah. Please continue, Evan.
Yeah. So once you've defined your block, you have to give a boundary name. Okay. Otherwise, you won't be able to add your boundary conditions or anything like that. You just have a simple block. So this is where your boundary comes into play. Okay. We can ignore edges for now. We'll not go too much into that. Edges basically help you create curves or any arcs or something like that. So if you want to create a circle, you can do that using this edge part. But again, edge to explain the whole thing, it will take another 15-20 minutes. So let's keep that on hold. So we'll go down to the boundary part. So boundary, you have again the moving wall, fixed wall, and front and back. Now in your boundary, we have to specify this. You know the right hand thumb rule, right? So you apply the boundary, you apply your face name or numbering based on the right and thumb rule. Now, in our case, we have the moving wall to the top, right? So over here we have the moving wall. So if I were to keep my hand on this top face with my thumb pointing outward and my fingers curling this thumb, okay, so we would have it curling this way. So you can say counterclockwise. Okay. So we would name this as 3762. That is the labeling scheme that we follow in block mesh. Okay. So that's why over here the numbering is 3762. Points number 3762 make up this particular face. This particular face is your moving wall. Then same goes for the fixed walls. Now this one, if my finger was pointing outward and my fingers are curling around it, it would be something like this, right? So if I'm looking at it, it'll look like clockwise. So it would be 0473. So it's 0473. Same for this side, it would be 2651. And if it's for the front or for the bottom face, it would be the same, like 1540. And for front and back, again, the same thing. It's just that this time the type will be empty because we are solving for a 2D case. It is your empty type is just that we are expanding the whole domain in the Z direction up to infinity. So that makes, in simple terms, your whole geometry a 2D geometry because we do not have any circulation or anything forming in that Z direction. If you were to solve for a 3D case, obviously this will change. You'll just put it as wall or patch or something like that. Okay. Now in our case, we have all of these as wall. You can change this to patch. There are multiple options. There is patch, there is symmetry, there is wedge. So in a wedge, when you have a circular domain, like if you have a pipe and you don't want to simulate the whole pipe because sometimes simulating the whole pipe might be computationally very expensive. So you only take a section of that pipe and you define it as a wedge. So you can do that whole thing. You can simulate that whole wedge with the properties of a whole pipe. Okay. So those are different types or ways you can model the whole thing. So depending on your use case, you can change those things. So this is about block mesh. Then, then we go to control dict. Again, as I said, this is where you will mention your start time, end time. Open it up, notepad. Yeah. So this is where you will mention your start time, end time, the application like icofoam. Then you would have end time step. If you were to introduce any post-processing data, like for an airfoil case, for all the people from aerospace engineering, if you want to find the coefficient of lift or drag, you can add those additional functions at the end of this control dict. Like you would have a functions part, like you would write functions, and then you would put a whole syntax block over there. So there are multiple ways to like those parameters and you can use to post process something. So if you want, you can remove the wall shear stress, or you can remove wall temperatures. You can remove coefficient of lift, drag, multiple parameters. So what we want to post process are always put within this control dict. So this is your control dict. Then we have FE schemes and FE solutions. I think Nikhil has already covered this. He had mentioned the Gauss linear and Gauss Seidel schemes and all of those. So here we are using the Eulerian scheme. So this one is a transient solver. That's why using Eulerian methods. If you were to use simple form, that is a steady state solver. So it would have the written steady state instead of Euler. So again, these are the FE schemes and solutions. In solutions, you mention your relaxation parameters. Any of these parameters if you want to tweak, like if you have some of your solutions diverging, we usually try to tweak all of these within this. You can add correctors, orthogonal correctors, and all of those. So if you have done already a basic CFD course, you will understand what are these doing and why we need to change some of them for a particular simulation. Okay. So once you're done with everything like this, you can now see this case does not have an all run file. So there is a thumb rule while running your case, anything in CFD or simulation. Okay. First, you start with the geometry, then you start with the mesh, then you go ahead with your simulation or the running of the simulation itself, and then you have your post processing. Okay, this is just a thumb rule. You can change it however you want. Sometimes you don't have to go by this whole thing. So what we'll do is first we will create the mesh. Okay. To create the mesh, you need to do block mesh. So that created my mesh. Now for a complex simulation, as Nikhil had, he would have done the decomposed part. So for those decomposition part, you require an additional file as well. You can't just simply, if I were to type decompose par simply like this, it would not understand because this decompose par dict is not mentioned. Okay. So you need to copy a few of these decompose if you want to run it in parallel, or if you want to just do any additional things, you need to have those particular files as well. Now, this is a pretty simple case, so we don't really need to decompose anything. So let's just start the simulation. So to start the simulation in OpenFOAM, you always type in the solver name that can be found in your control dict. So whenever you open your control, you can always scroll on top and you can see the application. So in this way, you know which solver you're solving and what type of physics you're going to solve. So it's a good idea to always check this part out. So we'll do icofoam and then you just run. Now it ran really fast because it's a very small case, simple case. And then you do parafoam to just visualize your data. Okay. Now, once it is open, we have on top, on the top left, you would have U, P and all that. This is where you can change the parameters you want to see. So we can see the whole simulation. Now this is your simulation. Okay. But you don't really understand where are the recirculation and all that. So to view all of those, Paraview itself has multiple ways to see that. So on the just from where you clicked your U option or your velocity or pressure, over here, just below that, you have a few of these options. Okay. You have stream tracers, you have glyphs, you have additional, like if you have a 3D simulation and you want to view what's going on inside your simulation, like inside the domain, you can use the slice option. There is another clip option. And if you can't really find any of these, you go to filter on top over here. You click on filter and you type search. You just click on search and then over here you can type. Like if I want to type, say, tracer. So I'll type tracer and it'll give me here the stream tracer. Double click it or click and then press enter and then click apply. Okay. Now, Nikhil also had done something similar to this. Now we have too many streamlines. So let's lower this a bit. So say from 1000, I'll make it down to 100 and I'll click apply. Now, currently you are, if you're doing this way, you are making or you are plotting those streamlines based on this line. But if you have a very, very long domain or a very large domain and you're trying to do this, it will always give you some errors or some weird spots. Okay. So there are different ways. You can either plot or you can remove the streamlines over this line, or on the left hand side for seed type, you have an option of point source. So this point source will just generate a sphere. You can change the radius of this sphere over here down. So over here, let's say we make the sphere to 1. Okay, so we've made the sphere like really big. So I think 0.5 will be better. Okay, so when you're doing this, just make sure that your domain is completely covered, or at least the areas of interest that you're trying to remove streamlines around are covered. This is really handy for 3D cases as well, because this line is just a 2D line, right? It's just from point A to point B, but this sphere is in complete 3 dimensions. See, if you see this, it's in 3 dimensions. So if you have a 3D geometry, like a flow over a cylinder, 3D cylinder, a flow over an aircraft or airfoil or something like that in a 3D simulation, you can view the whole glyphs around the whole thing, around the whole geometry. So you will see we don't really have any demonstration schedule for the 3D case because 3D cases do take a lot of time, but we have people who have already done most of the simulations, which are 3D simulations on our repo. So you can always check those also out. So, okay. So once we've done this, you can just hide this sphere, scroll in a bit and click on apply. Okay. Now 100 was really small. So let's bump it up back to 1000. Okay. So we have some problem. So say let's delete this one. Okay. Yeah. So we'll again do the streamlines. Go to point source. Increase this to 0. Sorry. This to 0.02 or 25. Okay. And 100. Okay. Yeah. Let's lower the spear. Okay. Yeah. So you see over here we have some circulation, but in streamlines, it will just give you how the flow is happening. It won't give you an arrow direction or where exactly is the flow starting from, where is it going. For that, you can use the glyph option. Okay. So let's hide this one and let's open our cavity case again. And this time instead of stream tracer, we will click the glyph option. So you can click on glyph and over here you can assign, like now it is set to arrow. Orientation, you can set the orientation to u, that is your velocity, how the velocity will flow. In that way, these arrows will orient themselves. And then you have the scale array. The scale will just increase. Like we know that over here, you will have the highest amount of flow looking at the legend and the whole simulation and contours itself. Whereas over here, you'll have lower number of, like you'll have a slower velocity. So it will orient based on that, the scaling. For now, we'll just keep the scaling to no scale array and click on apply. You see over here, let's change the color a bit. Yeah. So see over here on top, since this lid was moving, and then over here, once it is moving, the velocity that is entering into this cavity, it will hit this wall, then it is hitting this wall, and then so on and so forth, and it's just circulating within this whole domain. Now the same case, it is a transient solver. So until the simulation ends, it will keep doing this. Whereas for a steady state case, until it has like stabilized and everything is steady, it will give you your steady simulation case. And then once the whole domain is stabilized, it will stop the simulation. That is for a steady state case. So those are the basic difference between a steady state and a transient solvers or a transient simulation. So yeah, this is all about the cavity case in OpenFOAM 9. So the same, if you want to search tutorials in OpenFOAM 24.12, the path is a bit different. So under Ubuntu 22, this time instead of going to OPT, you can go down all the way to USR. And in this you have lib. Under lib, you scroll down, you can open OpenFOAM. And over here you will have your OpenFOAM 2412. Same now, over here you have. Now you see, if you compare this particular tutorial directory and you compare the OpenFOAM 9, OpenFOAM 2412 will have more tutorials, more solvers, better solvers. Like you will have multiple solvers that are more stable and all compared to OpenFOAM 9. So again, if you want to modify anything, you can go over here to application, you can go to solver, you can also change utilities and all of those solvers over here. Now in our OpenFOAM 9, we only had basic. Here you have acoustic solvers as well, combustion, compressible, DNS, then you have finite area, heat transfer, many solvers are there. So you're not bound to only be using OpenFOAM 9 for solver modification or something like that. You can use OpenFOAM 24.12 as well. So this was just a brief and basic overview of OpenFOAM and how exactly are you supposed to copy files, place them in which files, how you're supposed to run and the whole file structure and all that. So if you have any doubts, we'll be happy to take that now. Oh yeah, stop sharing. Okay. Okay. So most of the queries in the chat, Paris has answered. Okay. Okay, Paris has answered that one.
So this is the email ID of the CFD team of FOSSEE. Okay, if you, after this workshop, after we all log out, if you feel that you need to ask something, you need to post a question, you have any query, you can just drop an email and we'll get back to you. So all these 4 days, no, till Friday, we might be a little bit busy with this workshop. So next week, definitely we'll get back to you. And we'll also try to get back to you within this week. So just keep posting your queries here and we'll definitely get back to you. Okay, Dr. Shekhar has written he has asked a question, Evan.
Yeah, what solver is suitable for metal or polymer erosion? So for polymer erosion, mm, we haven't really tried any of those. Wait, just let me have a look. Erosion related, right? So you can try using one of the Lagrangian solvers because as Mr. Advait Gupta also said that they tried and they have used some of the modified Lagrangian approaches. So you can try using one of them depending on the case obviously you want to solve. Because we haven't really gone too much in detail about erosion and additive manufacturing as a whole. Okay, for practicing, can you send this? Okay. Yeah, so regarding recorded lecture and all this, I think after every session we do email the participants with your registered email ID. So you will get a link to all of these recordings and the YouTube link will be live by in a few weeks. It should go live. So you will be able to download the YouTube or you can watch it on YouTube itself. So those videos will be there. Our previous workshops also are there on YouTube. So you can always refer to those as well. Harshada, if you are planning to create your own solver, yes, the user bin, the way that you've written it is fine. Okay, Harshada, if you are not able to see your OpenFOAM directory, just check whether your installation is done properly. Because if you have installed it properly, you will have an OpenFOAM file at least in your OPT file folder.
Yes, I am having OpenFOAM file, but I am not able to see that OpenFOAM 9 and even though which version I have downloaded.
So have you downloaded any of the developer versions or the skeleton version? Because in those versions, you don't really get the tutorials. You can check which version, like OpenFOAM 9 is downloaded, yes, but just check the variant that you have downloaded in OpenFOAM 9 because there are specific versions for developers. There are specific versions in which you have just the skeleton, like you'll just have basic OpenFOAM files or libraries, and then you have the classic version that has all your tutorials and everything included. So just check which one have you installed. Okay, on the official website also you can search that. You can just type download Ubuntu Open or you can download OpenFOAM 9. You can click on for Ubuntu and then you can scroll down to their download page. On that, they've mentioned all the versions and the variations in that particular version. Yeah, Paris has also given you a command. You can try running that. Okay. So for all of you who are starting off with OpenFOAM, unless you try using OpenFOAM, you won't really understand what exactly is happening because you have to get your hands dirty with OpenFOAM. You will get multiple errors in the beginning, but those errors will only help you better understand what you are doing. Because even I've used ANSYS and all of those commercial softwares. The thing about using a commercial software and using an open source software is that when you're using an open source software, you are solely responsible for everything that you do. In ANSYS and in any of the commercial solvers, you can at least say that, okay, in the back end, you have this particular limitation, so you can't really do anything. But in OpenFOAM, you have that entire liberty. You have everything you can do. So if something goes wrong, you have to sit and you have to see where exactly is the error. And it's not like as I showed you in the when we're doing our solver modification, if you get an error, the terminal specifies in which particular file on what line you're getting that error. So you can go line by line and see why is that error popping up. And then you can solve that. And there are multiple videos on how to solve these errors as well. So you're not really stuck at that point. Okay. So don't think that OpenFOAM is really scary and just because there's a terminal and all, it becomes difficult to understand. No, it's not like that. And also we have been working on the front end for OpenFOAM at FOSSEE. So hopefully in the coming years, we will have at least a GUI for at least the basic stuff. So you don't have to really rely completely on knowing each and every command. It might become at one point like ANSYS, you can just click some buttons and you will get at least a desirable output. So yeah, if there is any more doubts, you can ask us. We are there here, or you can type it in the chat box as well, which was comfortable. So are all of you trying OpenFOAM right now? At least the tutorial, the IcoFoam tutorial. Okay, okay. So have all of you understood, or at least briefly understood, what we've done today from the solver modification to multiphase? At least for undergrad, multiphase might be a bit difficult, but for people who are in their master's and PhD, are you able to understand what we are doing? If there is any improvement or something like that, you can always let us know. Okay. Dr. Shekhar, you won't find OpenFOAM 2412 tutorials in OPT. You will have to scroll down to your USR folder. So wait, I'll share it again. So my screen is visible, right? Yeah.
Yes.
So for OpenFOAM, wait, I'll increase the size. Yeah. So if you're trying to see anything for OpenFOAM 24, so you will have to go down to USR, and inside that you have to go to lib. Okay, just simple lib, and scroll down to OpenFOAM. Okay, so over here we have OpenFOAM. Click on OpenFOAM, and over here you will find OpenFOAM 2412. Inside this you will have your tutorials. Okay. Yes, Shruti, you have a doubt for the morning session. What exactly is the doubt? Okay, so for people who want to learn about programming in OpenFOAM, there is a course by, not course you can say, but a YouTube playlist by Mr. Tushar Gohil. He has explained everything from basic on how to do programming in OpenFOAM, how to develop your own solver from scratch as well. So you can check those videos out. And there's also Wolf Dynamics. They also have some documentation on solver modification and solver development. So those are also good. You can also check out the official OpenFOAM page. They have multiple resources for solver development as well. So these three places are your go-to place if you're trying to, or at least beginning with OpenFOAM programming and solver development and all that. Okay, I'll share the links over here. 1 minute, just give me a minute. Okay. Okay, Payal ma'am has sent one link.
Yeah, the other links you can share even.
Yes, ma'am. Okay, Shruti, you have solved for T and U, and you have also run the solver, right? The compiled solver. But your pipe is not visible in Parafoam. Okay. Shruti, once you copied the 50 folder, like whatever files were there inside your 50 folder into the 0 folder, uh, the pipe geometry should still be created. Okay. Just try cleaning the whole case once again and see if that solves the issue. Try cleaning the whole case and run the whole simulation once more, because the pipe geometry should, if it is solving your equations and it is solving the whole simulation, your pipe geometry should be there. Otherwise, it would have thrown up an error at the very beginning if the geometry itself is missing. Or when you're loading it in Paraview, just check whether you're loading the proper file. Or you can manually do a touch.foam. You can create a file named .foam or something, and you can then open that in Paraview and see whether it is at least opening that particular file of yours in Paraview.
Hello, sir. Am I audible?
Yes, Shruti.
So can you please repeat it once again?
Okay, so try first cleaning the whole case. Do an all clean, like the bash all clean, which is already there in the file. Do that and run the simulation again and see if the simulation is giving any error. If it does not give you any error and it is running just fine, when you're opening it in Paraview, try to see whether the file that you opened is first of all correct or not. Like if is Paraview just not showing anything, or when you're clicking on apply, it is not showing anything.
So it's not showing anything, like the interface is getting open, but pipe is not visible. And even when I'm clicking on apply, nothing is visible.
Okay, but the file name is showing on the left hand side, right?
Yes, so file name has been shown.
Okay, so if nothing is showing, have you used Paraview before?
Yes, sir. For the demonstration, like when I downloaded the Ubuntu and then the Paraform, no, then at that time I tried, then there was a geometry visible.
Okay. Okay, you can try using Paraform built-in to just see if that solves the issue. I'll type the command.
Sir, I tried using Paraform built-in. There's nothing visible. But when I just type Paraform, then it gives an error.
Okay. Okay. But while it is running the simulation, that time it does not give you any error.
No, sir. When it's running in PowerShell, there's no error. It completes whole process.
Okay. Because if it is giving you an error at the very last step, that is at least in Paraview when you're opening it and then you're trying to load the case and it says it gives you some error in red, right? In one box down.
Yes, sir. Yes, sir. In box.
So that is most probably because some file is missing, like you have either given a wrong boundary condition or some of the things are interfering with each other, or but then that should always give you an error at the very beginning. Like if you are solving your simulation, that is the time when you will get that error itself in your terminal. When you
But sir, like
one minute, when you copied the 50 folder into your 0 folder, did you clear out the whole thing? Like, is scalar 1 and scalar 2 still there?
sir, in 0 folder, I kept scalar 1 and scalar 2 as it is. I just copied T and U.
T and U, right?
Yes, sir.
Okay. And okay, solve for, and before that, you already solved for U and for T.
Yes, sir.
And in the flow simulation, you've made those changes, right? You had to change the solver name also from simple form to scalar transport form.
Yes, sir, I have did that.
Okay, that is done. And then you've copied it into your folder. And that is running. You've already used the all run script only, even for the new scalar transport form.
Yes, sir.
Okay. Can you share a screenshot of what error you're getting on the email? We'll try to see what exactly the error, because if it is running, everything is running fine, but your geometry is not loading and Paraview is giving that error at that time. So we'll have to first check whether it is running the simulation properly itself or not. Some file might be missing. That is why Paraview is not loading it and it is just giving you that blank Paraview.
Okay, sir. So should I share the screenshot of Paraview?
Share a screenshot of Paraview also, and when your simulation is done, no, whatever commands you're getting or whatever is it's displaying in your terminal, once you've done your whole simulation, share a screenshot of that as well.
So should I rerun like simulation once again?
First, try rerunning it. If you're rerunning it properly and then it works fine, then it's not a problem. If it is still giving that error, then you give these two screenshots on email.
Okay, sir. So like when we complete for the T constant, no, after that we need to copy whole 50 folder into the steady scalar file, in 0 folder, right?
Yes.
And in 0 folder we need to delete rest of the things. We need to only keep the scale 1, scalar 2, and T and U.
Yes.
Okay, sir. The process is fine. I don't know where
You
the error is.
can either delete or you can just keep everything that is there. Like whatever you're copying from your 50 folder, just copy and paste the whole thing in your new scalar transport form case, and make sure that your scalar 1 and scalar 2 are there as an addition to the previous files. Okay, try
Sir,
that and
like
see.
when I'm doing for T, then I don't get any new file for scalar 1 and scalar 2. The scalar 1 and scalar 2 are already there in this steady scalar file. So
Yeah,
I'm
yeah.
not replacing scalar 1 and 2.
So you keep that scalar 1 and scalar 2 as it is, but just whatever is in that 50 folder, you just paste every single thing. Don't delete anything then.
Okay, sir. Okay, I'll do.
Yeah. Try that and see if that resolves the issue.
Okay, sir. Thank you, sir.
Okay.
So if there are no more questions, we can wind up, right? Evan, what do you say?
Yes, ma'am.
Okay, and other questions we can take up through the email that I have provided. And before leaving, everybody, please make sure that you have marked your attendance. So we will wait for another couple of minutes. We'll wait for another couple of minutes and then we'll log off for the day. Tomorrow we'll meet at 10 a.m. sharp. So Paris has given the link for marking your attendance once again. Those who have missed to mark yourselves present, please do it now. Okay, so I think we can wind up.
Yes, ma'am.
Yeah, thanks a lot. So tomorrow, please join a bit earlier. I mean, 9:55 or so, 9:59, right? So that we can, sorry, from 10:30. Hello. Yeah. So 10:20, 10:25, if you all join, then we'll start sharp at 10:30 tomorrow. And okay. So see you all. Thanks a lot for joining today.
Thank you, ma'am. Thank
Yeah,
you.
thanks. Bye-bye. Thanks a lot to Evan and Paris and Nikhil also for being there for the whole day. Thanks a lot.
Yes, ma'am.
Thanks to our studio team also. Okay, thanks. Bye-bye.